There was a time when the speed of light felt like the end of the story. For generations, humanity imagined a future in which every obstacle would eventually fall. Oceans had once seemed impossible to cross. Continents had once been separated by months of dangerous travel. Entire civilizations lived and vanished without ever knowing one another existed. Then ships arrived, then railroads, then aircraft, then spacecraft. Each breakthrough appeared to shrink the world. Every century seemed to carry the same lesson. Distance was merely a temporary problem. Given enough intelligence, enough patience, enough technology, humanity could eventually go anywhere. And so, when scientists discovered the ultimate speed limit of the universe, many people assumed the mystery was already solved. Light traveled at nearly 300,000 kilometers every second, almost unimaginably fast. Fast enough to circle Earth more than 7 times in a single second. Fast enough to reach the moon in little more than 1 second. Fast enough to cross the entire solar system in hours. Surely that would be enough. Surely any civilization capable of reaching light speed would eventually master the cosmos. It seemed obvious. But hidden beneath that assumption was a question that few people truly asked. What if light itself wasn't fast enough? Not merely inconvenient, not merely slow, fundamentally insufficient. The possibility sounds absurd at first. After all, light is the fastest thing known to exist. Nothing with mass can move faster. No signal can outrun it. No spacecraft can surpass it. Nature appears to have built reality around this limit. So how could the fastest speed possible still be too slow? The answer begins with a strange historical irony. For most of human history, the night sky looked small, not because it actually was small, but because human minds were never designed to comprehend astronomical distance. When ancient observers looked upward, stars appeared scattered across a dome, beautiful, mysterious, but nearby. Even after the invention of telescopes, the illusion remained. The stars seemed like destinations, places, locations, not vast abysses separated by distances so enormous that language itself struggles to describe them. Then the measurements began, one by one, painfully, slowly. Astronomers started discovering the true scale of the darkness. The nearest star beyond the sun was not thousands of kilometers away, not millions, not billions. It was more than 4 light years distant, a phrase that sounds harmless until you understand what it means. A light year is not a measure of time. It is a measure of distance. The distance light travels in 1 year, nearly 10 trillion kilometers. And the nearest star sits more than 4 of those away. Suddenly, the fastest thing in existence required years merely to reach our closest neighbor. Imagine shrinking the solar system into something familiar. Suppose Earth were the size of a marble. The sun would be a large beach ball. The planets would fit comfortably within a city. But the nearest star, it would be thousands of kilometers away. The scale isn't merely large, it is deceptive. Space hides its size behind emptiness. That emptiness became the first clue in a much larger mystery. Because once astronomers measured the distance to nearby stars, they naturally wondered about more distant ones. Then more distant still. Every answer revealed another layer. Each measurement expanded the universe. Each discovery pushed the horizon farther away. The cosmos seemed determined to grow faster than humanity's understanding of it, and something unsettling emerged from the data. The problem wasn't technology. The problem wasn't engineering. The problem wasn't energy. The problem was scale itself. Imagine achieving the impossible. Imagine building a spacecraft capable of reaching light speed. No fuel limitations, no mechanical failures, no political obstacles, no economic restrictions. You have conquered every challenge civilization has ever faced. Now the journey begins. You leave Earth. 1 second later, the moon is behind you. Minutes later, planets become distant points. Hours later, the solar system starts shrinking into darkness. Months pass. Then years. Eventually you arrive at the nearest star. Humanity celebrates. History changes forever. Yet something unexpected happens. The universe barely notices. The Milky Way contains hundreds of billions of stars. You have reached one. The cosmic ocean remains essentially untouched, like a sailor crossing a pond and discovering an entire planet covered by oceans. The achievement is extraordinary. The scale remains terrifying, and the deeper astronomers looked, the stranger the situation became. Because stars were only the beginning. Beyond the stars lay clusters. Beyond clusters lay spiral arms. Beyond spiral arms lay galaxies. Beyond galaxies lay immense structures stretching across the observable universe like ancient scars embedded within space-time itself. Each new layer expanded the mystery. Each new layer raised a troubling question. What if the universe was not merely large? What if it was so large that even light, the ultimate speed limit, was fundamentally inadequate for exploring it? At first, the idea seemed impossible. Then the numbers arrived. And the numbers told a story nobody expected. A story in which humanity's greatest dream was about to collide with the largest structure ever discovered. The Milky Way. And that was where the investigation truly began. The answer seemed obvious. It wasn't. The first maps of Earth were filled with empty spaces. Ancient cartographers sketched coastlines that faded into uncertainty. Beyond familiar territories, strange creatures lurked in the margins. Entire oceans existed as rumors. Vast continents remained hidden behind horizons no traveller had crossed. The unknown always seemed large, until it was measured. Then it became larger. Something remarkably similar happened when astronomers began mapping the Milky Way. At first, our galaxy appeared manageable. A collection of stars, a luminous river stretching across the night sky. Beautiful, certainly. Large, undoubtedly, but understandable. Then the measurements arrived, and the familiar picture began to fracture. The Milky Way is not simply a gathering of stars. It is a colossal structure spanning roughly 100,000 light-years from side to side. That number is easy to say. It is almost impossible to feel. Human beings evolved to understand distances measured in steps, roads, and journeys. Even continents challenge our intuition. 100,000 light-years belongs to an entirely different category of reality. Imagine standing on one edge of the galaxy. Now imagine a beam of light leaving your position. Not a spacecraft, not a probe, not a futuristic vessel. Light itself. The fastest traveller nature permits. That beam would need approximately 100,000 years to cross the Milky Way. 100,000 years. When that light began its journey, modern civilization did not exist. Agriculture did not exist. Cities did not exist. Writing did not exist. Entire human cultures still slept beneath prehistoric skies. Only now would the beam be reaching the opposite side. This was the first truly unsettling clue. Light speed sounds fast because human scales are tiny. The universe operates on scales so vast that even light begins to appear slow. Not slow in an everyday sense, slow in a cosmic sense, and the difference changes everything. For centuries, humanity imagined that the stars were destinations. Once rockets improved enough, we would simply travel to them. The challenge was technological, or so it seemed. But the Milky Way quietly revealed a deeper problem. The challenge was geographical. Reality itself was enormous. Consider our location. The solar system does not occupy some privileged central position. It sits inside a minor spiral structure known as the Orion Arm, a small branch within a galaxy containing hundreds of billions of stars. We are not at the center, not near the center, not even particularly important. We are residents of a quiet suburb in a city so vast that crossing it would require longer than recorded human history. That realization transformed the investigation, because once astronomers understood our position, a disturbing question emerged. What would happen if humanity actually achieved light-speed travel? At first, the answer sounded triumphant. We would spread among the stars, colonize neighboring systems, build civilizations across the galaxy, perhaps even unite the Milky Way into a single cosmic society. Science fiction had explored such visions for decades. The future seemed obvious. Then mathematicians examined the details, and the dream began to unravel. Suppose a civilization launched a light-speed vessel toward the galactic center. The destination would still be tens of thousands of light years away. Even moving at the absolute maximum speed permitted by nature, the voyage would require longer than all of recorded civilization. Entire empires would rise and collapse during the journey. Languages would evolve. Species might change. History itself would become unrecognizable. And this assumes perfect travel, perfect reliability, perfect survival. No interruptions, no accidents, no delays. Reality rarely grants such generosity. The implications were startling. A civilization capable of reaching light speed would not suddenly become free from distance. Distance would remain the dominant force, shaping its future. Like ancient sailors discovering that crossing one ocean only revealed another. But an even stranger clue was lurking beneath the numbers, because the galaxy is not static. Stars move, clusters migrate, orbits shift. The Milky Way itself rotates. Nothing remains fixed. The map changes while travelers move through it. Imagine trying to cross an ocean while every island drifts across the water. Every harbor shifts location. Every destination moves. That is closer to the reality of galactic travel. And yet, despite these enormous scales, the Milky Way is considered relatively small. That statement sounds absurd. How can something 100,000 light-years wide be considered small? The answer reveals the next layer of the mystery. Galaxies themselves are not the primary structures of the universe. They are components, building blocks, individual cells within something far larger. Astronomers slowly uncovered this truth during the 20th century. At first, many believed the Milky Way was the universe, a vast universe. Certainly, but the universe. Then telescopes improved. The distant smudges visible in photographs began revealing their identities. They were not clouds. They were not nebulae. They were galaxies. Entire galaxies, each containing hundreds of billions of stars, each separated from others by immense gulfs of darkness. Suddenly the Milky Way shrank, not physically, psychologically. A structure once thought enormous became merely one example among countless others. This was the second major shock. Humanity had not discovered a universe. Humanity had discovered one neighborhood, and the neighborhood stretched endlessly. The scale shift was devastating. Imagine believing your city is the entire world, then discovering there are billions of cities. That is roughly what happened to astronomy. Every answer created a larger question. Every discovery widened the mystery. The universe seemed determined to exceed expectation. But perhaps the strangest consequence involved communication. Travel is one thing. Conversation is another. Even if light-speed ships became possible, messages would still require years, centuries, or millennia to travel between distant regions. Civilizations separated by thousands of light years could never share a common present. They would live in different historical eras, despite existing simultaneously. One world might send a greeting. Another might receive it centuries later. Responses could take longer than entire civilizations survive. What would a galactic society even look like under such conditions? Could it exist at all? Or does the speed of light quietly prevent large-scale civilizations from ever forming? The possibility was unsettling. The universe might not merely be difficult to explore, it might be structured in a way that naturally fragments intelligence, isolating worlds, separating histories, creating invisible barriers stronger than any war. For a moment it seemed the mystery had revealed itself. The problem was distance. The universe was simply too large. Case closed. But then astronomers discovered something far worse. Distance was not the real enemy. Distance could at least be measured. Something else was hiding beneath it. Something moving through every galaxy, every cluster, every region of space. Something that would make even light speed seem inadequate. Space itself. And what scientists found next forced them to reconsider everything. For a brief moment, the mystery appeared solvable. The Milky Way was vast, extraordinarily vast, but it was still a place, a structure with measurable dimensions. Given enough time, enough patience, and enough technological advancement, Perhaps humanity could eventually explore it. Perhaps one day the stars would no longer feel distant. Perhaps light speed really was enough. That was the comforting conclusion. Then astronomers looked beyond the galaxy, and the comfort vanished. The first shock came from a simple realization. Galaxies are islands, not metaphorically, literally. Each galaxy is surrounded by an immense ocean of emptiness, an ocean so large that the spaces between galaxies often dwarf the galaxies themselves. This was not what scientists expected to find. Human intuition assumes that objects dominate space. We notice mountains, cities, forests, planets, the things. We rarely think about the emptiness between them, but the universe operates differently. The emptiness is the main feature. The structures are merely traces floating inside it. Imagine shrinking the Milky Way to the size of a dinner plate. Its neighbouring galaxy, the great spiral known as the Andromeda Galaxy, would not sit beside it. Not across the table, not even across a room. It would be several meters away. Everything between them would be empty, almost perfectly empty. The comparison is still misleading because it understates the situation. Human beings struggle to visualize true cosmic emptiness. Our world contains air, dust, clouds, molecule, noise. The space between galaxies contains almost nothing. It is not an ocean filled with water. It is an ocean filled with absence. And crossing that absence became the next clue in the investigation. At first, Andromeda seemed encouraging. It lies approximately 2.5 million light-years away, an astonishing distance, yet perhaps not impossible for an advanced civilization. After all, millions of years are immense. But the universe itself is billions of years old. Maybe truly ancient civilizations could undertake such journeys. Maybe light speed remained sufficient after all. Then astronomers expanded the map. Andromeda was not an exception. It was a neighbour. Beyond it lay thousands of galaxies. Beyond those lay millions. Beyond those lay billions. The observable universe was becoming crowded with structures, but those structures were separated by distances so enormous that language began to fail. The scale was growing faster than comprehension, one by one. Telescope surveys revealed a hidden architecture stretching across space. Galaxies clustered together, clusters gathered into larger groups. Groups connected through gigantic filaments. Filaments formed a cosmic web, a vast network spanning the observable universe. From a sufficient distance, the arrangement resembled neural pathways in a brain, or cracks spreading through ancient ice, or scars across an unimaginably large surface. The resemblance was eerie, not because the universe was alive, but because the patterns emerging from gravity produced structures of astonishing complexity. Yet another mystery appeared. If galaxies formed a cosmic web, what occupied the enormous regions between those filaments? The answer was unsettling. Almost nothing. Astronomers discovered gigantic voids, regions of space so empty they challenged belief. Some stretched hundreds of millions of light-years across. Entire cosmic deserts. Silent expanses where galaxies became rare. Where darkness dominated. Where a traveller could move for unimaginable distances without encountering anything significant. The existence of these voids changed the investigation. Until then, humanity's challenge had been reaching places. Now another question emerged. Why was so much of reality empty? Why build a universe whose dominant feature is absence? No one knew. The mystery remains unresolved. And buried within those vast voids was an implication that few people appreciated, even at light speed. Crossing one of these regions could require longer than the entire history of complex life on Earth. Imagine departing Earth before the first dinosaurs appeared. Imagine travelling continuously at light speed. Imagine finally arriving at your destination only after the dinosaurs had risen, dominated the planet, vanished, and been replaced by mammals. That is the scale involved, and yet the observable universe contains countless such distances. The numbers felt wrong, not mathematically wrong, psychologically wrong, as if reality had been constructed according to rules entirely indifferent to human expectations. The universe seemed almost hostile to exploration, not through violence, not through danger, through scale. Distance itself became a barrier, a silent wall extending across existence. But another puzzle was emerging, one that would eventually overturn everything scientists thought they understood. The clue came from light, once again. Light, the same messenger responsible for nearly everything humanity knows about the cosmos. Every galaxy ever observed, every star ever measured, every nebula ever photographed. All of it arrives through light. Ancient photons crossing unimaginable distances, travelers from forgotten eras in many ways. Astronomy is not the study of space. It is the study of old messages. Every observation is a historical document. When we observe the moon, we see it as it existed slightly more than a second ago. When we observe the sun, we see it 8 minutes in the past. When we observe Andromeda, we see it 2.5 million years ago. The deeper we look, the farther backward in time we travel. Astronomy became a form of archaeology, an investigation into ancient light, and this revealed something extraordinary. The universe visible to us is not the universe as it exists now. It is the universe as it used to be, a collection of historical snapshots, fragments, echoes, remnants. The night sky is a museum of vanished moments. At first, this seemed like an interesting curiosity. Then, scientists realized its implications. If light requires time to travel, then every observation is delayed. The farther away an object is, the older its image becomes. Simple enough. But what if the universe itself changes while the light is traveling? What if space evolves? What if galaxies move? What if reality transforms during the journey? Then observations become something stranger, not windows, artifacts. And that distinction would prove crucial because astronomers soon discovered evidence suggesting the universe was not static, not stable, not eternal. It was changing. Everywhere. All the time. The cosmic web itself was evolving. Galaxies were moving apart. Structures were drifting. The map was transforming. And if that was true, a disturbing possibility emerged. What if some destinations could never be reached? Not because they were too far away, but because the universe was carrying them away faster than travelers could pursue them. The idea sounded impossible. After all, nothing can move faster than light. Einstein had made that clear. The speed limit seemed absolute. Case closed, or so everyone thought. Then the evidence began to accumulate. Observations, measurements, patterns hidden within ancient starlight. The clues pointed toward a conclusion so strange that many scientists initially resisted it. Because if the interpretation was correct, the greatest obstacle in the universe was not distance. It was motion, and the thing moving was space itself. The real mystery was only beginning. The universe has a habit of turning certainty into evidence, again and again. Humanity builds a picture of reality, fits the pieces together, and believes the mystery is finally understood. Then a new observation appears, a forgotten clue, an unexpected signal, a tiny crack in the explanation, and through that crack, a much larger mystery emerges. By the beginning of the 20th century, astronomers believed they were approaching a complete understanding of the cosmos. The universe appeared stable, ancient, unchanging. Stars were born, lived, and died. Certainly, but on the largest scales, reality itself seemed fixed. Galaxies occupied their positions. Space provided the stage. Time marched forward. The cosmic structure remained essentially the same. It was an elegant picture. There was only one problem. The evidence disagreed. The first clues arrived quietly. They emerged from spectroscopy, a technique allowing astronomers to analyze light and determine how celestial objects move. Every atom leaves a signature, a fingerprint hidden within light. By examining these fingerprints, scientists could measure whether distant objects were approaching or receding. The method worked beautifully. Nearby stars revealed their motions. Galaxies revealed theirs. The universe was finally speaking. What it said was unexpected. Almost every distant galaxy appeared to be moving away. Not some, not many. Almost all of them. At first, researchers suspected mistakes. Instruments fail. Data can deceive. Observations sometimes create illusions. But the pattern persisted. The farther away a galaxy appeared, the faster it seemed to be retreating. The relationship was unmistakable. Distance and recession were linked. The cosmos was expanding. The discovery felt almost absurd. Expanding into what? That was the immediate question. If the universe grows larger, what exists beyond it? What contains it? What surrounds it? The answers were deeply unintuitive. According to the emerging picture, the universe was not expanding into anything. Space itself was stretching. The distinction sounds subtle. It changes everything. Imagine dots drawn across the surface of a balloon. As the balloon inflates, every dot moves away from every other dot. No dot occupies the center. No dot is moving across the surface. Instead, the surface itself expands. Distances increase automatically. The galaxies behave similarly. They are not racing through space like ships crossing an ocean. The ocean itself is growing, and that realization transformed the investigation. Because if space expands, then distance becomes a moving target. A destination does not simply wait for you, it drifts. The farther away it is, the faster the separation grows. At first this seemed inconvenient, but manageable. After all, expansion appeared relatively slow. The nearest galaxies remained reachable in principle. The local universe still felt navigable. Then astronomers pushed their observations deeper into the darkness. The results were disturbing. The expansion was not slowing down, it was accelerating. That discovery landed like a shockwave. For decades, scientists assumed gravity should gradually reduce cosmic expansion. Galaxies attract one another. Mass pulls on mass. The universe should eventually slow its growth. Perhaps it might even collapse someday. The logic seemed reasonable. The calculations appeared straightforward. Reality disagreed. In the late 20th century, observations of distant exploding stars revealed something nobody expected. The expansion of the universe was speeding up, not decreasing, increasing. It was as though an invisible force lurked beneath reality, pushing galaxies apart, a hidden engine driving the cosmos outward. Astronomers gave this mystery a name: dark energy. The label sounds dramatic. In truth, it reflects ignorance. Dark energy means we do not know what is causing the acceleration. We see the effect. The cause remains hidden, and buried within that uncertainty was a terrifying implication. The universe was not merely large, it was becoming larger, constantly, relentlessly, every second, every minute, every year. The cosmic map was stretching beneath our feet. Suddenly, the challenge of exploration became stranger. Imagine standing on a moving walkway in an airport. You can walk forward, but the walkway carries your destination away. If it moves slowly, you still arrive. If it moves fast enough, you never reach the end. Now imagine the walkway extends across billions of light years. That is closer to the situation astronomers were uncovering. The farther a galaxy lies from us, the faster cosmic expansion increases the distance. Eventually, a threshold appears. Beyond that threshold, recession outpaces any possible pursuit. Even light cannot catch up. This statement sounds like a contradiction. Nothing moves faster than light. Einstein made that clear. Yet here was evidence suggesting distant galaxies recede faster than light itself. Had physics broken? Not exactly. The galaxies are not moving through space faster than light. Space between them is expanding. Einstein's speed limit applies to motion through space-time. It does not prohibit space-time itself from stretching. The distinction is subtle. Its consequences are enormous. Entire regions of the universe may already be permanently unreachable. Not difficult to reach, not technologically challenging, fundamentally inaccessible. Forever. This realization created one of the strangest horizons in science. Not a physical wall, not a boundary made of matter, a limit created by the expansion of reality itself. Beyond that horizon, Destinations retreat faster than any signal can pursue. Messages never arrive. Travelers never reach them. Information never returns. It is as though portions of existence are slipping into a permanent shadow. At first glance, this sounds like the solution to the mystery. Light speed isn't enough, because expansion keeps carrying distant regions away. Case closed. But this was only the first layer. The true implications ran much deeper, because astronomers began asking a more unsettling question. What happens in the far future? Expansion is occurring today. Acceleration is occurring today. What about billions of years from now? The calculations painted an eerie picture. Over immense stretches of time, more galaxies disappear beyond the cosmic horizon, one by one, cluster by cluster. Civilizations born trillions of years in the future may look into the night sky and see almost nothing. The evidence for the wider universe could vanish, not because the universe disappeared, because the light can no longer reach them. Imagine being born inside a cosmic prison without realizing it. Imagine seeing only your local galaxy and assuming it is all that exists. Future astronomers may face exactly that situation. The greatest discoveries of modern cosmology could become impossible. The evidence itself may fade away. That possibility transformed the mystery yet again. The universe was not merely difficult to explore, it was actively hiding portions of itself. Reality contained horizons beyond which knowledge could not pass, invisible boundaries woven into space-time. And if that was true, another question emerged, a far more troubling question. How much of the universe has already vanished beyond our reach? How much reality exists forever beyond observation? How many galaxies are currently hidden behind horizons we can never cross? The numbers were staggering, but before scientists could understand what had been lost, they first needed to understand the speed limit itself. Why does light occupy this privileged position? Why does nature enforce such a boundary? And what hidden consequences emerge from trying to approach it? The answer would lead directly into the heart of Einstein's universe. And there, another assumption was waiting to break. The mystery was only getting larger. Long before humanity dreamed of interstellar empires, there was a simpler mystery, a beam of light. At first, light seemed ordinary. It illuminated landscapes, cast shadows, reflected from water, filled the night sky with stars. For centuries, it appeared to be just another phenomenon waiting to be understood. Then, scientists began measuring it, and the measurements created a puzzle so strange that it threatens to unravel physics itself. The problem emerged from motion. Common sense suggests that speeds should add together. If you throw a ball from a moving train, the ball inherits some of the train's speed. Everything behaves this way. Cars, aircraft, ships, projectiles. Motion stacks upon motion. The logic seems unavoidable. So what happens if you chase a beam of light? The answer should have been straightforward. Yet every experiment pointed toward the same impossible conclusion. No matter how fast the observer moved, light always appeared to travel at exactly the same speed. Not approximately, exactly. The results seemed absurd. Imagine running toward an approaching train. The train's relative speed changes. Imagine driving toward a storm. The storm's apparent motion changes, but light refused to cooperate. Its speed remained fixed. Nature was protecting something. Scientists simply didn't know what. The mystery lingered for years. Then, in 1905, a young patent clerk named Albert Einstein followed the implications wherever they led. The conclusion was astonishing. The speed of light was not adapting to observers. Reality itself was adapting. Space changed. Time changed. Distance changed. The universe was rearranging itself to preserve a single fundamental rule. The speed of light must remain constant. Everything else became negotiable. This was not merely a scientific discovery. It was a revolution in the structure of existence. The familiar universe quietly dissolved. A stranger universe emerged. Imagine reality as a giant fabric woven from space and time together, not separate entities, not independent dimensions, a single interconnected structure. Move slowly through that fabric and life appears normal. Move faster and subtle distortions emerge. Move faster still and the distortions become profound. Clocks slow, distances contract. Time itself begins behaving differently. These effects sound like science fiction. They are measurable facts. Astronauts experience tiny versions of them. Particles accelerated near light speed demonstrate them constantly. The universe keeps careful records. Every experiment confirms the same story. Einstein was right. Yet buried within relativity was another clue. A clue directly connected to our investigation. The closer an object approaches light speed, the harder it becomes to accelerate further. At first, the increase is manageable. Then it grows and grows and grows. The required energy begins rising dramatically. Imagine pushing a cart. Initially, it moves easily, but with every additional increase in speed, the cart somehow becomes heavier. Not literally heavier, functionally heavier, more resistant, more demanding, more expensive to accelerate. Near light speed, the situation becomes extreme. The energy requirement climbs toward infinity. The barrier becomes absolute. This is why no object with mass can reach light speed. Not because engineers lack imagination, not because technology remains primitive, because reality itself appears structured to prevent it. The speed limit is not merely practical, it is fundamental. And for a while, this seemed to settle the issue. Light speed was the fastest possible velocity. Case closed. The mystery solved. But, as often happens in science, the answer created a larger question. Why this limit? Why not twice as fast? Why not 10 times faster? Why not infinite speed? The universe could have been designed differently, yet somehow reality selected this specific value, and the consequences ripple through everything. Stars, galaxies, black holes, communication, causality, even the order of events. The speed of light acts less like a speed limit and more like the architectural framework of existence. Remove it and reality may become unrecognizable. But another strange implication soon emerged, one that initially sounded encouraging. From the traveler's perspective, approaching light speed changes the experience of distance. Imagine a voyage to a distant star. Observers on Earth might measure years passing, but aboard the spacecraft, time slows relative to the outside universe. The travelers experience a shorter journey. The effect becomes stronger as speed increases. Near light speed, distances in the direction of travel appear compressed. Space itself seems to shrink. At first glance, this sounds like an escape route. Perhaps the universe is not truly inaccessible. Perhaps relativistic effects solve the problem. Perhaps travelers can cross enormous distances within a single lifetime. For a moment, it appeared the investigation had found its breakthrough. The barrier remained. Yet relativity seemed to offer compensation. A clever loophole hidden inside the equations. A cosmic balancing act. The universe limits speed, but reduces subjective travel time. Maybe that was enough. Maybe humanity could still reach the stars. Maybe the mystery was finally unraveling. Then another complication emerged, one that transformed the entire discussion. Because travel time for the traveler is not the same as travel time for civilization. Imagine departing Earth for a galaxy millions of light years away. Relativity may reduce the journey from your perspective. You might age only years, perhaps decades. But when you arrive, millions of years have passed outside your spacecraft. Everything familiar is gone. Every city, every nation, every language, every memory. Earth itself may have changed beyond recognition. You arrive successfully, yet you arrive in a future disconnected from the civilization that launched you. This transformed intergalactic travel from an engineering challenge into a philosophical one. What does it mean to explore the universe if every destination exists in a different epoch? What does colonization mean if communication becomes impossible? What does connection mean when time itself separates societies? The deeper scientists examined relativity, the stranger the implications became. Distance was no longer the only obstacle. Time had joined the investigation. The two could not be separated. Space and time were partners in the same mystery, and hidden within their relationship was an even larger revelation. Because if relativity changes time, then observations themselves become complicated. Every glimpse of the cosmos becomes entangled with history. Every photon becomes a message from another era. The universe was no longer merely large, it was temporally fragmented. Different regions existed in different visible ages. Reality resembled a vast archive of overlapping historical moments. And that raised a haunting question. If light requires time to travel, and if the universe is expanding, and if distant regions are slipping beyond reach, how much of reality are we actually seeing? And how much remains permanently hidden? The answer would reveal that the observable universe is not the universe itself. Not even close. What astronomers discovered next forced them to confront a possibility more unsettling than any distance. The majority of reality may lie forever beyond observation. And if that is true, light speed isn't merely too slow. It may prevent us from ever seeing most of existence at all. The answer created a bigger question. The most dangerous assumptions in science are often the invisible ones, not the ideas we debate, not the theories we challenge, the assumptions so deeply embedded that nobody notices them. For centuries, humanity carried one such assumption without realizing it. If something exists, then eventually it can be reached. Perhaps not today. Perhaps not tomorrow, but someday. Given enough time, enough knowledge, enough determination, any destination should ultimately become accessible. It is a profoundly human belief. The belief that reality is open, that mysteries can be solved, that frontiers can be crossed. The universe appeared to encourage this optimism. Every generation pushed farther than the last. Maps expanded. Horizons retreated. Unknown regions became familiar territory. The pattern seemed universal. Then cosmology discovered something disturbing. The pattern breaks. Not everywhere can be reached. Not everything can be observed. Not every mystery can be solved. Some portions of reality appear permanently beyond contact, and the reason lies hidden within the structure of the observable universe itself. The phrase sounds straightforward. Observable universe. Most people hear it and assume it refers to everything that exists. It does not. That misunderstanding conceals one of the strangest discoveries in modern science. The observable universe is not the universe. It is merely the portion whose light has had time to reach us. That distinction changes everything. Imagine standing in a vast forest at night, holding a lantern. The illuminated region is visible. Beyond the light lies darkness. The darkness may contain trees, rivers, mountains, entire landscapes. Their existence does not depend on your ability to see them. They simply remain beyond illumination. The observable universe functions similarly. Light travels at a finite speed. The cosmos has existed for a finite amount of time. Therefore, there is a limit to how far information could have traveled since the beginning. Anything beyond that limit remains unseen, not because it does not exist, because its light has not arrived. This realization initially seemed manageable. The universe is about 13.8 billion years old. Therefore, we should see roughly 13.8 billion light years in every direction. Simple. Elegant. Wrong. Astronomers quickly discovered a complication. While light was traveling toward us, the universe continued expanding. Space stretched beneath the photons. Distances increased. Destinations moved. The result is profoundly counterintuitive. The most distant objects we observe today are not merely 13.8 billion light years away. Many now reside tens of billions of light years from Earth. The observable universe spans roughly 93 billion light years across, a number so enormous that it barely registers as meaningful. And yet even this staggering volume represents only what we can see, not what exists. That distinction became the next major clue, because once scientists accepted the observable universe as a limited region, a larger question emerged. What lies beyond it? The honest answer remains deeply unsatisfying. Nobody knows. Not because the question lacks importance, because the evidence cannot reach us beyond the observable boundary. Light has not arrived. Signals have not arrived. Information has not arrived. The region may contain galaxies, clusters, structures unlike anything we have observed, or perhaps conditions entirely different from our cosmic neighborhood. We simply do not know, and this ignorance is not temporary. That is the critical detail. Many scientific mysteries eventually yield to better instruments, more data, new experiments. This situation may be different. The limitation is built into space-time itself. The universe appears to contain regions fundamentally disconnected from us. Not difficult to access, not technologically challenging, disconnected. The distinction matters. Imagine living inside a vast mansion. Thousands of rooms extend beyond your location, yet every corridor leading toward them continuously lengthens faster than you can walk. No matter how long you travel, you never arrive. The rooms exist. They remain forever inaccessible. That analogy approaches the reality astronomers have uncovered. The universe contains regions that can influence us only if information reaches us. If expansion prevents that information from arriving, causal connection disappears. Two locations may exist within the same universe, yet remain permanently isolated. A remarkable possibility, and a deeply unsettling one, because it forces us to reconsider what we mean by the universe. When people imagine the cosmos, they often picture a single connected structure, a vast but unified reality. Yet cosmic expansion suggests something stranger. Reality may be partitioned into enormous domains separated by horizons no signal can cross. Isolated regions drifting apart forever, like islands disappearing into a growing fog. The implications extend far beyond exploration. They affect knowledge itself. Consider what science fundamentally requires: evidence, observation, measurement. Without those ingredients, theories become speculation. The scientific method depends upon contact with reality. But what happens when reality contains regions beyond observation? What happens when entire portions of existence cannot provide evidence? A boundary emerges. Not a technological boundary, an epistemological boundary. A limit on knowledge itself. For perhaps the first time in history, humanity encountered a mystery that may remain permanently unsolved. Not because we are insufficiently intelligent, because the universe may be structured in a way that prevents complete understanding. That realization felt almost philosophical. Then astronomers discovered evidence making it even stranger. The observable universe itself contains clues that something larger exists beyond its horizon. Subtle clues, ancient clues, patterns hidden in the oldest light ever detected. The clues came from the cosmic microwave background, the faint afterglow of the early universe, a relic from a time when stars did not yet exist, when galaxies had not formed, when reality looked unimaginably different. This ancient light became a cosmic fossil, a remnant of infancy preserved across billions of years. Scientists examined it carefully, searching for irregularities, searching for traces, searching for fingerprints left behind by the earliest moments of existence. And they found something remarkable. The observable universe appeared astonishingly uniform, far more uniform than expected. Regions separated by immense distances shared nearly identical properties. Temperatures matched, structures aligned, patterns repeated. It was as though distant parts of the cosmos somehow coordinated with one another long ago. But how? How could regions now separated by billions of light years have exchanged information? How could they become so similar? The mystery became known as the horizon problem, and solving it would require a radical new idea. An idea suggesting the observable universe is merely a tiny fragment of something vastly larger. A fragment so small that our entire cosmic horizon might represent only a microscopic patch of a greater reality. If true, the implications were staggering. Everything humanity has ever observed, every star, every galaxy, every cluster, every black hole, every known structure, might constitute only a tiny visible remnant of a universe extending far beyond our reach. And if most of reality lies beyond observation, another question immediately follows. How can we understand a cosmos we cannot fully see? That question would drive scientists toward one of the boldest theories ever proposed, a theory that seemed to explain everything for a while. Then new mysteries appeared. The answer seemed obvious. It wasn't. The universe does not simply separate places. It separates moments. This distinction is easy to miss because human experience rarely encounters it. When two people speak across a room, the delay is negligible. When someone calls another continent, communication feels immediate. Even signals traveling through satellites appear nearly instantaneous. Distance exists, but time hardly notices. The cosmos operates differently. In the universe, every conversation becomes an archaeological event. Every message arrives from the past. Every observation is delayed. Every exchange occurs across layers of history. And once astronomers began thinking about communication rather than travel, a new mystery emerged. Perhaps the greatest obstacle facing an advanced civilization is not reaching distant worlds. Perhaps it is talking to them. Imagine that humanity discovers intelligent life orbiting a star 100 light-years away. The announcement would transform history. The question would be obvious. What do we say? The answer would matter less than people imagine, because the real challenge begins after the message is sent. The signal travels outward, year after year, decade after decade. A century later, it arrives. If the civilization responds immediately, another century passes before humanity receives the reply. A simple greeting requires 200 years. One question, one answer. 2 centuries. An entire political era could begin and end between sentences. Civilizations might transform completely before a conversation progresses beyond introductions. The implications are profound. Interstellar communication is not merely slow, it operates on historical timescales. Imagine writing a letter and knowing that your great-great-grandchildren may receive the response. That is closer to the reality of cosmic dialogue, and 100 light-years is considered nearby. The Milky Way spans roughly 100,000 light-years. Messages crossing substantial portions of the galaxy would require tens of thousands of years. Entire cultures could emerge, flourish, collapse, and vanish before receiving a reply. This changed the investigation dramatically. Until now, the mystery centered on transportation. Could light speed carry us far enough? Now another question emerged. Even if travel becomes possible, can civilizations remain connected? Or does the speed of light naturally fragment intelligence across the galaxy? The possibility sounded almost tragic. The universe might contain countless civilizations, yet each could remain isolated inside its own bubble of time, not separated by space alone, separated by history. A civilization receiving a signal from another world would never encounter that society as it exists now, only as it existed centuries or millennia earlier. Every communication becomes a message from ghosts. This idea feels abstract until viewed through a familiar analogy. Imagine receiving a live broadcast from ancient Rome, not a reconstruction, not a historical document, an actual transmission. You watch senators debate, merchants trade goods, citizens walk crowded streets. To you, the events are happening now, yet everyone involved has been dead for thousands of years. That is how cosmic communication functions. The farther away the source, the deeper into history you look. Astronomy had already revealed this truth through observation. Communication merely exposes its consequences, and buried within those consequences was another clue, one connected to a famous mystery, the mystery of silence. For decades, scientists have asked a deceptively simple question. If intelligent life is common, where is everybody? The universe is old, extremely old. Stars began forming billions of years before Earth existed. If even a tiny fraction produced technological civilizations, some should possess immense age advantages over humanity. Thousands of years, millions of years, perhaps hundreds of millions of years. Such civilizations could accomplish feats beyond imagination. Yet the sky remains silent. No confirmed signals, no verified contact, no evidence of galactic societies. The contradiction became known as the Fermi paradox, a puzzle named after Enrico Fermi, who famously asked a simple question: where is everybody? Many explanations have been proposed. Perhaps intelligent life is rare. Perhaps civilizations self-destruct. Perhaps technological species lose interest in expansion. Perhaps they communicate in ways humanity cannot detect. Each possibility carries unsettling implications. Yet the speed of light introduces another possibility. Perhaps the galaxy is not empty. Perhaps it is disconnected. Imagine thousands of isolated communities scattered across an immense continent. Communication between them requires centuries. Travel requires millennia. Coordination becomes impossible. Awareness becomes limited. Each community develops independently. Most never discover the others. The Milky Way may function similarly. Not a unified civilization, not a coherent network, a collection of isolated historical islands. This possibility gained attention as scientists began modeling realistic galactic societies. The results were surprising. Even advanced civilizations struggle to overcome the tyranny of light-speed delays. The galaxy may simply be too large for meaningful centralization. No emperor could govern it. No government could coordinate it. No culture could remain synchronized across such distances. History would diverge too quickly. Communication would lag too severely. The dream of a unified galactic civilization began to look increasingly unrealistic. At first glance, this seemed to solve the puzzle. The speed of light creates isolation. Case closed. But another complication appeared, one that made the silence even stranger, because communication delays explain isolation. They do not explain complete absence. Even if civilizations cannot converse efficiently, they should still leave traces, signals, megastructures, artifacts, evidence, something. Yet astronomers continue finding nothing definitive, and this led researchers toward an unsettling realization. Perhaps communication itself changes as civilizations advance. Think about humanity. Just a century ago, powerful radio transmissions leaked into space continuously. Broadcast towers illuminated the planet with detectable signals. To distant observers, Earth might appear increasingly visible. But technology evolves. Modern communication uses focused transmissions, fiber optics, efficient networks. Leakage decreases. The planet becomes quieter. Paradoxically, technological advancement can make a civilization harder to detect. The more advanced it becomes, the less obvious it appears. This introduced another layer to the mystery. Maybe the galaxy contains civilizations hidden by efficiency, not broadcasting, not announcing themselves, quiet. Invisible, like cities concealed beneath fog. The possibility was intriguing, yet it failed to address a deeper issue. Even perfect communication cannot overcome cosmic expansion, and beyond the Milky Way expansion becomes dominant. The communication problem transforms into something worse. Messages do not merely take longer. Some destinations become permanently unreachable. Signals sent today will never arrive. Replies can never return. Entire galaxies are drifting beyond contact. Not slowly, relentlessly. Every year, more regions cross horizons from which communication becomes impossible. The universe itself is severing connections, one by one, like an ocean swallowing islands beneath rising tides. The image is haunting, yet it reveals something important. The cosmos does not simply challenge exploration, it challenges relationship, connection, awareness. The ability of one region of reality to know another. And that realization pushed the investigation toward a disturbing possibility. Maybe the greatest limit imposed by light speed is not travel. Maybe it is loneliness, cosmic loneliness, a universe so vast that even intelligence struggles to bridge its divisions. But just as this conclusion began to settle into place, another discovery appeared, a discovery that seemed to offer a way out. For a moment, it looked like the mystery might finally be solved. The optimism would not last. For a while, the numbers appeared reassuring. The universe was vast, unimaginably vast. Communication delays were severe. Distances stretched beyond intuition. Entire civilizations might live and die before receiving a reply from distant worlds. Yet none of these obstacles seemed fundamentally impossible. Difficult, certainly. Slow, undoubtedly, but not impossible. And that distinction mattered, because throughout history, humanity has repeatedly overcome problems that once appeared insurmountable. Mountains became roads, oceans became trade routes, the sky became an air corridor, again and again. Barriers eventually yielded to persistence. Perhaps cosmic distance would do the same. Perhaps the solution was simple. Wait long enough. This became one of the most attractive answers to the mystery. If the universe is old enough, even light-speed expansion through the galaxy should eventually succeed. Imagine a civilization with patience measured not in decades, but in millennia, or millions of years. Such a civilization would think differently, plan differently, act differently. A journey requiring 10,000 years might seem extravagant to humans. To a civilization enduring for millions of years, it could appear routine. The scale changes. The challenge shrinks. At first glance, the argument seemed powerful. Consider the Milky Way. Although crossing the entire galaxy requires roughly 100,000 years at light speed, colonization need not proceed in a single leap. The civilization could expand gradually, star by star, system by system, each newly settled world launching further missions, like seeds carried across a continent. Researchers modeled this process. The results were surprising. Even moving well below light speed, a determined civilization could theoretically spread throughout the galaxy within a few million years. A long time by human standards. A brief interval compared to the galaxy's age. The Milky Way is more than 13 billion years old. A few million years is a tiny fraction of that history. Suddenly the mystery seemed less threatening. Perhaps light speed was sufficient after all. Perhaps the galaxy was conquerable. Perhaps humanity merely needed time. The conclusion felt satisfying. Too satisfying. And science has a habit of becoming suspicious whenever answers arrive too neatly, because hidden inside the argument was an assumption so subtle that many people overlooked it. The assumption that the galaxy remains available indefinitely, that destinations patiently wait, that opportunities remain open forever. The universe had other plans. The first complication emerged from stellar evolution. Stars are not eternal. Every star possesses a lifespan. Some burn for billions of years. Others survive only millions. Eventually, fuel runs low. Fusion ceases. Transformation begins. Entire planetary systems change. Habitability shifts. Potential colonies vanish. Destinations evolve while travelers move toward them. The map refuses to remain fixed. This alone complicated long-term expansion. Yet the deeper problem lay elsewhere, beyond individual stars, beyond galaxies, beyond even the cosmic web itself. The universe was aging, and aging changes possibilities. Imagine exploring a vast library while sections are continuously removed, shelves disappear, books vanish, entire rooms become inaccessible. Your ability to explore depends not only on speed, but also on timing. Arrive too late and the opportunity is gone. Astronomers began realizing the universe behaves similarly. The cosmos of today is not the cosmos of the distant future. Expansion continues. Acceleration continues. Horizons continue growing. Accessibility continues shrinking. The universe is not simply large, it is dynamic. That distinction destroyed the comforting assumption, because waiting does not merely grant more time. Waiting also changes the conditions. Every delay carries consequences. A civilization postponing exploration may discover that some destinations have already slipped away forever. This realization led researchers to a remarkable concept: the cosmic event horizon. The name sounds technical. Its implications are profound. An event horizon marks a boundary beyond which information cannot return. Black holes possess such horizons, but cosmology revealed something astonishing. The universe itself may possess one, a horizon generated not by gravity, but by expansion. Beyond that boundary, galaxies recede so effectively that communication becomes impossible. No signal sent today can establish lasting contact. No expedition can permanently reconnect separated regions. Reality fractures into causal domains. At first, this seemed like a distant concern, a problem for unimaginably remote futures. Then, calculations revealed something surprising. The process is already happening right now. Galaxies are crossing these limits. Light emitted today from certain regions will never reach us. Messages sent toward those regions will never arrive. The separation has already become permanent, not because of technology, because of space-time. The discovery transformed the investigation. The issue was no longer whether humanity could travel far enough. The issue was whether reality itself permits access. Some destinations may have already been lost. Not destroyed. Lost. A subtle but crucial distinction, like ships vanishing beyond the horizon while continuing to exist elsewhere. This was the first major false ending of the mystery. For a brief moment, patience appeared to solve everything. The galaxy could be explored, the stars could be reached, the future seemed open. Then expansion revealed another layer. The universe does not simply reward patience, it punishes delay, and that changed the entire picture. Yet even this revelation failed to uncover the deepest truth, because the event horizon raised another question, a disturbing question. If galaxies are disappearing beyond reach, how many have already vanished? The observable universe contains hundreds of billions of galaxies, but is that the full inventory, or merely the surviving visible fraction? Astronomers began examining the earliest light in existence for clues. Ancient photons, cosmic fossils, messages from epochs so remote they border on incomprehensibility. Those messages suggested something extraordinary. The observable universe may represent only a tiny visible patch of a vastly larger reality. Not slightly larger, not moderately larger, potentially incomprehensibly larger. The implications were staggering. Everything humanity has ever observed could be analogous to a single grain of sand on an endless shoreline. A fragment, a remnant, a trace. The thought felt almost excessive. Surely reality could not be that large. Surely there must be some limit, some boundary, some final scale. Then astronomers followed the evidence, and the evidence pointed toward one of the most radical ideas ever proposed. A theory suggesting that the observable universe is merely the aftermath of an event so violent, so immense, and so ancient that it reshaped our understanding of cosmic reality. For a while, that theory seemed to answer everything. Then it created an even bigger mystery. What happened next changed everything. The clue was hidden in plain sight. For decades, astronomers had been staring directly at it. Every telescope, every observation, every map of the cosmos contained the evidence. Yet its significance remained buried beneath the sheer scale of the universe. Sometimes mysteries persist, not because information is missing, but because the implications are too large to notice. The expanding universe was already a profound discovery. Galaxies moving apart, space stretching, reality evolving. Most scientists initially viewed expansion as a feature of the cosmos. Important, certainly, but ultimately manageable. Then they began calculating what expansion actually does over immense periods of time. The results were unsettling. Expansion is not simply movement, it is separation. And separation accumulates. Imagine drawing two dots on a rubber sheet. Stretch the sheet slightly. The dots move apart. Stretch it again. They separate further. Repeat the process endlessly. Eventually, the distance becomes enormous, despite neither dot moving across the surface. This simple image captures something fundamental about our universe. The cosmos is not merely growing, it is continuously increasing the separation between regions of reality. And that growth creates a wound, a hidden wound spreading through space-time itself. Not a wound of destruction, a wound of disconnection. The consequences emerge slowly enough that human intuition rarely notices them. Stars remain visible. Galaxies still fill telescope images. The night sky appears stable. But stability is an illusion created by short timescales. Viewed across billions of years, the picture changes dramatically. The universe resembles a great continent breaking apart, not suddenly, gradually, relentlessly, piece by piece. Astronomers began exploring what this process means for the future. At first, the answers seem straightforward. Galaxies drift farther apart. Travel becomes harder. Communication becomes slower. Nothing especially surprising. Then another realization appeared. Expansion does not affect all structures equally. Gravity fights back. Within galaxies, gravity remains strong enough to hold stars together. Within galaxy clusters, gravity often preserves large-scale structure. These regions remain connected, for now. Beyond them, expansion dominates. The distinction creates a remarkable cosmic landscape. Imagine cities connected by roads. Inside each city, life continues normally. Buildings stand. People interact. Commerce thrives. But the land between cities continuously stretches, roads lengthen, travel times increase. Eventually, the cities become isolated. Each survives. The network disappears. That analogy closely mirrors the future astronomers were uncovering. Local structures endure. Large-scale connectivity erodes. Reality becomes fragmented. And this fragmentation carries profound implications. Because science often assumes the universe can be understood as a whole, a single, coherent system, a unified reality. But expansion suggests something stranger. The universe may increasingly behave as a collection of isolated islands, each possessing only partial access to the larger cosmos. This realization transformed the mystery from one of transportation into one of perspective. What can a civilization know if most of reality eventually disappears from view? The question became more than theoretical. Researchers began modeling the distant future, trillions of years ahead, far beyond the lifespan of stars like our Sun. The predictions were astonishing. Future observers living inside the Milky Way's descendants may see no external galaxies at all. The evidence for cosmic expansion itself could vanish. The evidence for the Big Bang could vanish. The evidence for a larger universe could vanish. Future astronomers might conclude that their galaxy constitutes the entire cosmos, not because they are careless, because critical evidence would no longer be observable. This possibility remains one of the strangest conclusions in modern cosmology. Scientific understanding depends upon timing. Humanity may live during a uniquely privileged era, a brief window when enough evidence remains visible to reconstruct cosmic history. Before that window opened, intelligent observers may not have existed. After it closes, critical clues may disappear forever. We occupy a narrow moment between ignorance and erasure. The realization feels almost eerie, as though the universe briefly reveals its secrets before withdrawing them again. And that led to another question. If observations depend upon timing, how much has already been lost? How much information vanished before humanity appeared? The universe existed long before Earth formed, long before the solar system existed, long before life emerged. Entire epochs unfolded without witnesses. Stars formed and died. Galaxies collided. Structures evolved. Histories vanished. The majority of cosmic events occurred before observers arrived to record them. Astronomy, therefore, resembles forensic investigation. Scientists reconstruct forgotten events from surviving traces. A photon here, a spectrum there, a faint signal crossing billions of years. The universe rarely provides complete records, only fragments, only clues. And among those clues, one stood above all others, a faint glow filling the entire sky, a glow so ancient that it predates galaxies themselves. The cosmic microwave background, this ancient radiation, appeared to preserve a snapshot of the early universe, a photograph from infancy. For decades, it became one of cosmology's most valuable pieces of evidence. Scientists hoped it might finally explain why the observable universe looks the way it does, and in many respects, it did. The microwave background revealed remarkable uniformity. The early universe appeared astonishingly smooth. Regions separated by enormous distances shared nearly identical temperatures, nearly identical properties, nearly identical conditions. At first glance, the observation seemed encouraging. The cosmos possessed order, consistency, predictability. Then someone asked a simple question: how? How could distant regions become so similar? Light requires time to travel. The early universe had limited time available. Many regions should never have exchanged information. They should not know about one another. They should not possess matching properties. Yet somehow they did. The contradiction became impossible to ignore. The evidence seemed self-consistent. The explanation was missing. This puzzle evolved into one of the greatest mysteries in cosmology, and solving it required a hypothesis so radical that many physicists initially struggled to accept it. The proposal suggested that before the observable universe existed in its current form, something extraordinary occurred, something unimaginably violent, something unimaginably brief, an event that expanded reality itself at a rate dwarfing anything observed today. If the theory proved correct, then the observable universe was not merely part of a larger cosmos. It was the aftermath of an explosion of space so extreme that ordinary intuition completely fails. The theory appeared elegant, powerful, perhaps even final. For a moment, scientists believed they had found the answer. They hadn't. Because hidden inside the solution was another mystery, one far larger than the original problem. The answer created a bigger question. The theory arrived with extraordinary confidence. For years, cosmologists had wrestled with contradictions hidden inside the early universe. The observable cosmos appeared too smooth, too uniform, too coordinated. Regions separated by immense distances somehow shared nearly identical properties. It was as though distant portions of reality had secretly communicated long before communication should have been possible. The evidence demanded an explanation. Then, in the early 1980s, a remarkable idea emerged: cosmic inflation. The proposal was deceptively simple. Before the universe became what we recognize today, space experienced an episode of expansion so extreme that ordinary language struggles to describe it. Not millions of years, not thousands, not even seconds, a tiny fraction of a second, an unimaginably brief event. Yet during that fleeting instant, the universe expanded by a staggering amount. Regions once close together became separated across enormous distances. The observable universe emerged from a tiny connected patch that had sufficient time to equalize its properties before inflation stretched it apart. The horizon problem appeared solved. The mystery seemed finished. Scientists celebrated. The theory explained multiple puzzles simultaneously. Uniformity, flatness, large-scale structure. Everything fit together elegantly. For a while, inflation looked like the missing piece, the first complete answer. But science rarely rewards certainty for long, because once researchers explored inflation more deeply, something unexpected appeared. The solution itself contained a hidden door, and beyond that door waited a much larger mystery. To understand why, imagine inflating a balloon. As the balloon grows, any small patch on its surface appears flatter and smoother. The larger the balloon becomes, the less curvature is visible locally. Inflation operates similarly. The observable universe may represent only a tiny patch of a vastly larger structure, a microscopic fragment of something much greater. At first, this conclusion felt harmless. After all, larger structures had appeared repeatedly throughout the history of astronomy. Earth became one planet among many. The solar system became one system among billions. The Milky Way became one galaxy among countless others. Why should the observable universe be different? Then physicists followed the mathematics further. The implications became extraordinary. Some versions of inflation suggested that expansion might not stop everywhere simultaneously. Instead, inflation could continue indefinitely in other regions, creating new cosmic domains, new observable universes, again and again, an endless process, a self-reproducing reality. The idea became known as eternal inflation. And if it is correct, the observable universe is not merely part of a larger cosmos, it may be one bubble among countless others, a tiny island in an unimaginably vast sea. The scale escalation was staggering. For centuries, humanity struggled to comprehend the size of Earth, then the solar system, then the galaxy, then the observable universe. Now even the observable universe risked becoming a local structure, a neighborhood, a fragment, a single chapter in a larger story. The mystery was expanding faster than understanding, and hidden inside this expanding picture was another consequence, one directly connected to our investigation. Because if inflation created a reality vastly larger than the observable universe, then most of existence may forever remain inaccessible. Not because of distance alone, because of expansion. Many regions may already be receding faster than light relative to us. Their information can never arrive. Their history can never be reconstructed. Their existence can only be inferred indirectly. Imagine living inside a lighthouse during a storm. The beam illuminates a small circle of ocean. Beyond that circle lies darkness. You know more ocean exists. You know ships may exist. You know entire coastlines may exist. Yet the beam never reaches them. The observable universe functions similarly. Everything beyond the cosmic horizon exists in a realm permanently hidden from direct observation. And as expansion accelerates, the illuminated region effectively shrinks relative to the larger cosmos. The universe is not merely large, it is disappearing, slowly, silently, continuously. This realization produced one of the strangest images in modern cosmology: galaxies slipping into shadow, not physically vanishing, not being destroyed, simply crossing horizons beyond which their light can no longer maintain contact. A gradual retreat into invisibility, a cosmic fading. Consider a distant galaxy emitting light today. That light begins traveling toward Earth. The journey seems straightforward, but meanwhile, space continues expanding. The destination moves. The route stretches. The photon struggles against a changing landscape. In some cases, the light eventually arrives. In others, expansion wins. The signal never reaches us. The message is lost forever. This means that every moment information is effectively being removed from potential observation, not from existence, from accessibility. The distinction is crucial. Reality continues. Knowledge diminishes. The universe contains more than we can ever know, and the gap grows. For centuries, science operated under a comforting assumption. Given enough time, unanswered questions eventually become answerable. Cosmology challenged that assumption directly. Some questions may lack accessible evidence, not temporarily, permanently. Entire regions of reality may lie forever beyond investigation. The implications extend beyond astronomy. They touch philosophy, epistemology, even the meaning of knowledge itself. Can something be considered part of science if direct observation is impossible? What counts as evidence when horizons prevent measurement? How should investigators treat realities that can only be inferred? These debates continue today. No consensus exists. And perhaps that uncertainty is appropriate, because the mystery remains unresolved. Yet another clue was emerging, one hidden within the galaxies themselves. Astronomers noticed that cosmic expansion creates an unexpected historical effect. Looking farther into space means looking farther into the past. This fact had been known for decades, but its deeper consequences were only beginning to emerge. The most distant galaxies do not appear as they exist now. They appear as they existed billions of years ago. The observable universe therefore resembles a time machine, a layered archive, a collection of historical records preserved in light. The farther outward we look, the farther backward we travel. Eventually, observations reach epochs before galaxies existed, before stars existed, before atoms fully formed. Each layer reveals another chapter of cosmic history. And this raised a remarkable possibility. Perhaps humanity cannot explore the entire universe physically, but perhaps we can reconstruct its history through ancient light. Perhaps observation can succeed where travel fails. For a moment, the idea felt promising. A new path forward, a new solution to the mystery. If light speed prevents direct exploration, maybe archaeology can replace it. Maybe the universe leaves enough traces behind. Maybe history itself becomes the map. Then a troubling realization appeared. History also has limits. Even ancient light cannot reveal everything. There are eras hidden behind deeper barriers, moments forever concealed from observation. And beyond those barriers lies one of the greatest mysteries in all of science. The question of what happened before the universe became visible at all. The mystery was only beginning. Every investigation eventually reaches a boundary, a point where the evidence becomes sparse, where certainty begins to dissolve, where the map ends. For explorers crossing oceans, the boundary was the horizon. For archaeologists, it is the disappearance of artifacts. For detectives, it is the final surviving witness. Cosmology has its own horizon, and unlike most boundaries in history, this one may never be crossed. For centuries, humanity imagined that better tools would solve every mystery. Build a larger telescope, construct a more powerful observatory, gather more data, push farther. The pattern worked remarkably well. Each new instrument revealed previously hidden worlds. The telescope expanded the solar system. Radio astronomy revealed invisible galaxies. Space telescopes uncovered structures billions of light years away, again and again. Technology seemed to move the horizon outward. Then astronomers encountered a limit that technology alone cannot overcome. The observable universe, not a wall, not a shell, not a physical barrier, a limit imposed by time, light, and the history of the cosmos itself. At first glance, this sounds disappointing, but the reality is stranger, because the observable universe is not merely a region of space. It is also a region of time. When we look outward, we look backward. The two are inseparable. The farther away an object lies, the older the information we receive. Eventually, the journey into distance becomes a journey into cosmic infancy. And there, at the deepest visible layer of reality, astronomers discovered something extraordinary. A glow, faint, uniform, ancient. The cosmic microwave background. This radiation fills the entire sky, not concentrated in one direction, not originating from a single object, everywhere. A silent remnant of the early universe. A fossil preserved from a time roughly 380,000 years after the Big Bang. To human intuition, 380,000 years sounds ancient. Cosmologically, it is almost nothing. The universe was still an infant. Stars had not yet formed. Galaxies had not yet emerged. Planets did not exist. Life did not exist. The cosmos looked utterly alien. Yet, somehow, traces of that era survive. Every radio telescope capable of detecting the microwave background effectively listens to an ancient echo, a message from a vanished epoch. The discovery was revolutionary. Suddenly, humanity possessed a direct glimpse into the distant past. A photograph of cosmic childhood, a snapshot from near the beginning. For many scientists, this felt like the ultimate achievement. Surely this was as far back as observation could reach. Surely the mystery was nearly solved. Then another question emerged. What existed before the microwave background? The answer revealed a deeper boundary. The early universe was not always transparent. Before those first 380,000 years, reality resembled a dense plasma, a hot fog of charged particles. Light could not travel freely through it. Photons scattered constantly. The cosmos was opaque. Imagine trying to see through a hurricane made of fire. No image survives. No clear observation escapes. The universe effectively hid itself. This created what astronomers sometimes call the cosmic fog. A barrier not of distance, but of visibility. Everything before it remains concealed behind a curtain of plasma. The microwave background marks the moment the curtain lifted. The instant the universe became transparent enough for light to travel long distances. And this realization transformed the investigation. The observable universe does not begin at the Big Bang. It begins at the oldest light capable of reaching us. An important difference, because beyond that boundary lies a chapter of history we cannot observe directly. The earliest moments, the first fractions of a second, the era when inflation may have occurred, the era when fundamental forces separated, the era when reality itself acquired its modern structure. These events shaped everything that followed, yet they remain hidden. Scientists infer them indirectly, like detectives reconstructing a crime from footprints and scattered evidence. The clues exist. The scene itself has vanished. At first, this seemed manageable. After all, science frequently studies inaccessible events. Geologists reconstruct ancient continents. Paleontologists reconstruct extinct ecosystems. Cosmologists could do the same. Then researchers notice something unsettling. The closer they approach the beginning, the less certain the evidence became. The laws of physics themselves began to strain. The familiar frameworks weakened. The equations grew incomplete. Gravity resisted unification with quantum mechanics. Space and time became difficult to describe. The deeper investigators looked, the more reality appeared to dissolve into unanswered questions. The mystery was not shrinking. It was growing. And buried within that growth was another revelation, one directly connected to our original question. Why isn't light speed enough? The answer was evolving. At first, the problem seemed geographical. The universe was simply too large. Then expansion complicated the story. Then horizons appeared. Then invisible regions emerged. Now a new limitation revealed itself. Observation itself has boundaries. Even perfect travel cannot recover information hidden behind the cosmic fog. Even perfect telescopes cannot directly image eras beyond transparency. Certain chapters of reality may remain permanently inaccessible, not because humanity lacks intelligence, because the universe guards them behind fundamental barriers. This realization created a subtle shift in perspective. For most of history, people imagined exploration as movement. Travel farther, see more, learn more. Cosmology suggested something different. Knowledge is not limited only by where we can go. It is limited by what reality allows us to observe. And reality may not be fully observable. The implications were profound. Imagine reading a book with missing pages. The story continues. Characters appear. Consequences unfold. Yet, critical chapters have been removed. You can infer what happened. You can estimate. You can model. But certainty remains elusive. The universe may function similarly. We possess fragments, powerful fragments, enough to reconstruct remarkable histories. Yet gaps remain. And those gaps matter, because hidden within them may lie answers to the deepest questions ever asked. Why does the universe exist? Why does space expand? Why does dark energy accelerate reality? Why does the speed of light possess its particular value? Why do the laws of physics take their current form? The clues exist. The complete answers remain hidden, at least for now. And just when it seemed that the observable horizon represented the ultimate limit, astronomers uncovered another possibility. A possibility suggesting that ancient light contains far more information than anyone realized. The oldest photons in existence might not merely reveal the past. They might preserve traces of events that occurred before the visible universe itself emerged. If true, the investigation was about to take a dramatic turn. The answer seemed close, but the real mystery was only beginning. Imagine discovering a library older than every civilization that has ever existed. A library older than Earth, older than the Sun, older than the Milky Way itself in its present form. A library whose pages were written before planets formed, before oceans existed, before life took its first uncertain steps. At first, such a place sounds impossible, yet, in a sense, astronomers have already found it. The cosmic microwave background is not merely ancient light. It is an archive, a vast historical record filling every direction of the sky. And within that archive may be hidden clues to mysteries far older than humanity. For decades, researchers treated the microwave background as evidence supporting the Big Bang, a remarkable achievement in its own right. The radiation matched theoretical predictions. Its temperature aligned with expectations. Its existence confirmed that the universe had once been hotter, denser, and dramatically different. Case closed. Or so it seemed. Then astronomers began examining the archive in greater detail, and the archive started whispering secrets. The first surprise emerged from tiny imperfections. The microwave background appears remarkably uniform, yet it is not perfectly uniform. Small fluctuations exist, minute differences in temperature, variations so subtle that detecting them required extraordinary instruments. At first glance, the irregularities seemed insignificant. Noise, tiny statistical deviations, nothing more. Then researchers realized those imperfections were the seeds of everything. Every galaxy, every star, every planet, every black hole, every living organism, all emerged from those ancient fluctuations. The structures filling today's universe began as faint ripples preserved within primordial light. The discovery was profound. The cosmos possessed memory. Modern structures could be traced backward to tiny patterns imprinted near the dawn of observable history. The universe was leaving clues about its own origins, and that transformed the microwave background from evidence into testimony, a witness statement from infancy. The deeper scientists listened, the more intriguing the testimony became, because some patterns appeared difficult to explain. Most observations aligned beautifully with inflationary cosmology. Yet a few anomalies lingered, subtle irregularities, unexpected alignments, features that stubbornly resisted easy interpretation. None proved new physics. None overturned established theory. Yet they remained. Small, unresolved traces hiding within the oldest observable light. And mysteries have a habit of gathering around unresolved traces. Some researchers proposed statistical coincidence. Others suggested observational limitations. Still others wondered whether the anomalies hinted at processes occurring before inflation. The debate continues. No consensus exists. But the existence of the debate reveals something important. Even our oldest evidence remains incomplete. The archive contains clues, not certainty. And that distinction became increasingly significant as cosmologists pushed deeper into the investigation, because another question emerged. What if light itself preserves information from epochs earlier than the microwave background? At first glance, the idea appears impossible. After all, the plasma era prevented photons from traveling freely. The cosmic fog blocked direct observation. How could information survive? The answer involves a different messenger, not light. Gravity. Einstein's theory predicts the existence of gravitational waves, ripples propagating through space-time itself. Unlike photons, gravitational waves interact extremely weakly with matter. They can travel through environments that trap ordinary light. They pass through stars, through gas, through plasma, through entire galaxies, almost undisturbed. This property transformed them into potential archaeological tools. If primordial gravitational waves exist, they may carry information from epochs hidden behind the cosmic fog, messages older than the oldest visible light, evidence from times previously considered inaccessible. The possibility electrified cosmology. For the first time, scientists glimpsed a potential route beyond the observable light horizon, a way to investigate eras previously buried beneath the earliest visible chapter of cosmic history. The implications were enormous. If detected, primordial gravitational waves could reveal whether inflation occurred, how inflation occurred, perhaps even what preceded it. The archive would suddenly become much larger. The missing pages might begin reappearing. For a moment, it seemed the mystery was approaching resolution. Then reality complicated the story again. Detecting such signals proved extraordinarily difficult. The universe is filled with gravitational noise. Colliding black holes, merging neutron stars. Countless astrophysical processes generate overlapping ripples. Separating primordial signals from later contamination became an immense challenge. Several apparent breakthroughs emerged. Several apparent detections generated excitement. Then further analysis introduced doubts. The pattern was familiar. Discovery, interpretation, complication, new mystery, science advancing through uncertainty. The investigation continued. And while researchers searched for ancient gravitational echoes, another realization emerged. One connected directly to our original question about light speed, because even if gravitational waves reveal earlier epochs, they do not eliminate cosmic horizons. They do not reconnect inaccessible regions. They do not overcome expansion. The fundamental limitation remains. Information travels, but information travels at finite speeds. Reality preserves boundaries. The deeper investigators looked, the clearer this became. The universe is not merely a place. It is an information system. Every observation depends upon signals. Every signal requires time. Every delay shapes knowledge. And once information becomes inaccessible, entire regions of reality effectively disappear from scientific reach. Not from existence, from evidence. The distinction appeared repeatedly throughout cosmology. Galaxies slipping beyond horizons. Ancient epochs hidden behind plasma. Potential universes beyond observation. Reality seems structured around informational limits, and this insight led to a remarkable shift in perspective. Perhaps the mystery was never truly about travel. Perhaps it was about information. Imagine possessing an infinitely fast spacecraft. Even then, knowledge remains constrained by what information exists and what signals survive. Observation becomes the ultimate currency. Without information, exploration loses meaning. The speed of light matters because it governs the flow of information itself, and that realization transformed the entire investigation. The question was no longer, can humanity travel far enough? The deeper question became, can humanity ever know enough? The distinction sounds subtle. It changes everything, because the limits of travel are engineering problems. The limits of knowledge may be woven into reality itself. For centuries, science advanced under the assumption that more observation eventually solves mysteries. Yet cosmology increasingly suggested that some mysteries may outlive observation. Some truths may remain permanently beyond evidence, not because they are false, because the universe withholds access. The idea was unsettling. Yet another possibility soon appeared, one that seemed to challenge these limits entirely. A possibility involving shortcuts through space-time itself. Warp drives, wormholes, exotic geometries, concepts once confined to science fiction. For decades they were dismissed as fantasies. Then physicists began discovering that reality might not reject them outright. For a moment, it looked as though the universe had finally revealed an escape route. But the deeper researchers investigated, the stranger the mystery became. The next discovery would change everything. By this point in the investigation, the pattern seemed unavoidable. Every apparent solution eventually revealed a deeper limitation. The galaxy was too large. Then the universe became larger. Expansion created horizons. Ancient epochs vanished behind cosmic fog. Information itself appeared constrained. Again and again, the mystery grew. And yet, one possibility refused to disappear. A possibility so compelling that it has haunted physics for generations. What if the speed limit could be bypassed? Not broken, bypassed. The distinction matters. Einstein's theory forbids objects from moving through space-time faster than light. But does it forbid space-time itself from behaving differently? For decades, the question lingered at the edge of theoretical physics, part curiosity, part speculation, part desperate hope. Because if some loophole existed, the consequences would be extraordinary. The observable universe might become accessible. Galaxies could reconnect. Cosmic isolation might end. Humanity could step beyond the prison of distance. At first glance, the idea seemed hopeless. Nature had repeatedly reinforced the speed limit. Every experiment confirmed relativity. Every observation supported Einstein's framework. The barrier appeared absolute. Then physicists noticed something strange. Space itself does not obey all the rules imposed on objects within it. This fact had already appeared during our investigation. Cosmic expansion stretches space. Distant galaxies recede effectively faster than light. Not because they move through space-time too quickly, because space-time itself changes. The distinction opened a door, a small door, a dangerous door, but a door nonetheless. If space-time can expand faster than light, perhaps it can be engineered. Perhaps distance itself can be manipulated. Perhaps the limitation is not velocity. Perhaps the limitation is geometry. The realization was profound. For centuries, travel meant movement. Go faster. Build stronger engines. Increase speed. Relativity suggested a different approach. Instead of moving through space, change the shape of space. Imagine standing on a moving walkway. Ordinarily, reaching a distant location requires walking. Now imagine folding the walkway itself. Suddenly, distant points become neighbors. No increase in speed is necessary. Geometry does the work. This simple analogy captures the essence of a remarkable idea proposed in the 1990s. The concept became known as the Alcubierre warp drive, named after physicist Miguel Alcubierre. The proposal emerged directly from Einstein's equations, not outside them, not in violation of them, inside them. According to the mathematics, space-time could theoretically be compressed ahead of a spacecraft and expanded behind it. The vessel itself remains locally stationary, yet the surrounding geometry moves, like a surfer riding a wave. The spacecraft never exceeds light speed within its local region. The wave carries it. The implications were astonishing, at least on paper. Distances measured in light years might be crossed rapidly. Galactic exploration could become realistic. The speed barrier appeared vulnerable for the first time. News headlines celebrated. Science fiction erupted with enthusiasm. The mystery seemed close to resolution. Then physicists examined the details, and the celebration faded. The first problem involved energy, not ordinary energy, exotic energy. The equations required negative energy densities, a form of matter energy never observed in the quantities necessary for a warp drive. Tiny quantum effects exhibit limited negative energy behavior. Nothing remotely approaching the required scale has ever been found. The amounts involved were absurd. Early estimates exceeded the mass energy of entire planets. Some calculations exceeded the energy content of stars. Later refinements reduced the requirements. The fundamental challenge remained. Warp drives appeared mathematically possible. Physically achievable was another question entirely. The distinction reopened the mystery. Yet another apparent solution was slipping away. Then another idea emerged, even older, even stranger: wormholes. The concept sounds almost mythical. A tunnel connecting distant regions of space-time, a shortcut through geometry. Two locations separated by enormous distances, linked through a hidden passage. Imagine drawing two dots on a sheet of paper. Travelling normally requires crossing the space between them. Now fold the paper until the dots touch. The journey becomes almost instantaneous. Wormholes operate according to a similar principle, at least conceptually. And remarkably, Einstein's equations again permit such structures. Not necessarily realistic ones, but mathematical solutions exist. For decades, wormholes occupied an uncertain position, not forbidden, not confirmed. A possibility suspended between physics and imagination. Their existence transformed the discussion, because suddenly the central mystery changed. Perhaps light speed isn't too slow. Perhaps light speed governs only ordinary routes. Extraordinary routes might exist. The universe could contain hidden pathways, buried corridors, forgotten tunnels woven into space-time itself. The idea felt almost magical, yet it emerged from serious physics, and that made it difficult to dismiss completely. For a brief moment, the investigation appeared to have reached a breakthrough. The speed limit remained, but geometry offered alternatives. Distance itself might be negotiable. The universe might contain shortcuts. The answer seemed close. Then another complication appeared, a devastating one, because theoretical possibility does not guarantee stability. Researchers discovered that many wormhole models suffer catastrophic problems: quantum instabilities, energy constraints, collapse mechanisms. Even if a wormhole forms, keeping it open may require exotic conditions no known process can sustain. The same issue haunted warp drives again and again. Reality permitted intriguing mathematics while withholding practical implementation. The pattern was becoming familiar. A doorway appears. A closer inspection reveals another lock. Yet despite these setbacks, something important had changed. The investigation no longer focused solely on distance. A deeper realization had emerged. The true obstacle may not be speed. It may be space-time itself. Distance exists because space-time possesses a particular geometry. Horizons exist because space-time expands. Isolation exists because information follows space-time's rules. Every limitation traced back to the same source, the structure of reality. And once scientists recognized this, a new suspect entered the investigation. Not distance, not speed, not even expansion, time. Because hidden inside every attempt to overcome cosmic separation was a more fundamental mystery, a mystery concerning the nature of temporal reality itself. And the next discovery would force investigators to confront it directly. The answer created an even larger question. At the beginning of this investigation, the villains seemed obvious. Distance. The stars were too far away. The galaxies were too widely separated. The universe was too large. Everything pointed toward geography. Now the evidence was telling a different story. Distance was only the symptom. The deeper cause appeared elsewhere, hidden beneath every journey, embedded within every observation, lurking inside every photon that crossed the cosmos. Time. Not time as human beings experience it, not clocks on walls, not calendars, something deeper, something woven directly into the architecture of reality. The realization emerged gradually, like a suspect appearing repeatedly at different crime scenes. At first, investigators overlook the pattern. Then suddenly, it becomes impossible to ignore. Every major mystery encountered so far contained a temporal component: communication delays, ancient light, relativity, expansion, cosmic horizons. All of them involved time, not incidentally. Fundamentally, the farther astronomers looked, the more reality seemed organized around temporal separation. The universe was not merely spread across space, it was spread across history, and that distinction changed everything. Imagine two civilizations separated by 10 billion light years. At first glance, the obstacle appears spatial, a problem of distance. Yet observation reveals something stranger. Each civilization sees the other as it existed billions of years ago. Neither can observe the other's present. Each sees a ghost, a historical remnant, an echo. The separation is not merely geographical, it is temporal. Reality itself distributes information through time. This idea sounds abstract, until one realizes that every observation works the same way. Look at the moon. You see it slightly in the past. Look at the sun. You see it minutes ago. Look at a distant galaxy. You see an ancient version. Astronomy is fundamentally the study of delayed reality. The night sky is not a picture of what exists now. It is a mosaic of different eras, different ages, different moments layered together. The universe resembles a museum whose exhibits come from wildly different periods of history. One display originates seconds ago, another millions of years ago, another billions. Everything appears together. Nothing is simultaneous. The realization was profound. Human intuition assumes a shared present, a universal now. The cosmos does not appear to provide one. Einstein's relativity had already hinted at this. Observers moving differently can disagree about the timing of events. What appears simultaneous from one perspective may not appear simultaneous from another. Time becomes relative, not absolute. At first, this seemed like a technical detail, a subtle feature of physics. Then cosmology exposed its deeper implications. The universe may not possess a single universal present at all. The idea is unsettling because it conflicts with ordinary experience. Human beings live immersed in the illusion of now. The present feels obvious, immediate, shared. Yet modern physics suggests otherwise. The cosmos contains countless local presents. No master clock coordinates them all. No universal timestamp labels reality. The implication transformed the investigation. Perhaps light speed is not merely a speed limit. Perhaps it is the mechanism preserving causal order, a safeguard protecting the structure of time itself. Imagine information traveling infinitely fast. Events could influence one another instantaneously across arbitrary distances. The concept sounds convenient, yet relativity reveals disturbing consequences. Cause and effect begin to blur. Different observers may disagree about which event happened first. Paradoxes emerge. The logical structure of reality weakens. The speed limit suddenly appears less arbitrary, more necessary, as though the universe deliberately restricts information flow to preserve consistency. This was an extraordinary shift in perspective. For centuries, people viewed light speed as a frustrating limitation. Now it appeared almost protective, a hidden rule preventing deeper chaos. The barrier was not imprisoning reality, it was organizing it. But if that was true, another question immediately followed. Why does time behave this way at all? Why should causality require such restrictions? Why should information possess finite speed? The answers remain uncertain, and uncertainty creates opportunity for mystery. Some physicists argue that space-time itself may not be fundamental. Perhaps space and time emerge from something deeper, a hidden layer beneath reality, an underlying structure from which familiar physics arises. The idea sounds radical, yet it has gained increasing attention because many of modern physics' greatest puzzles cluster around space-time. Quantum gravity, black holes, cosmic origins all point toward gaps in understanding. The familiar framework works extraordinarily well, yet it may not be the final story. Imagine studying waves on an ocean without knowing water exists. The waves appear fundamental. Only later does a deeper layer become visible. Some researchers suspect space-time may occupy a similar role, an emergent phenomenon, not the foundation, a consequence. If true, the implications are staggering. Because the limitations we attribute to space-time, including the speed of light, might arise from deeper principles, the investigation would shift again. Beyond stars, beyond galaxies, beyond the observable universe, toward the foundations of existence itself. For a moment, this seemed like pure speculation. Then, black holes entered the story, and black holes have a remarkable habit of turning speculation into evidence. For decades, they appeared to be simple endpoints, collapsed stars, gravitational traps. Interesting but isolated phenomena. Modern physics revealed something far stranger. Black holes may function as laboratories, exposing the hidden relationship between space, time, information, and reality. The clues are extraordinary. Information appears tied to surfaces rather than volumes. Entropy behaves unexpectedly. Quantum mechanics and gravity collide. Some researchers even suggest that space-time itself emerges from informational relationships, a breathtaking possibility. If correct, the speed of light may represent something deeper than velocity. It may describe the maximum rate at which reality can process information, the maximum rate at which causality can propagate, the maximum rate at which existence can update itself. The idea remains speculative, yet it illustrates how dramatically the investigation has evolved. We began asking whether light speed was fast enough to cross the universe. Now we are asking why light speed exists at all. The mystery has shifted from engineering to ontology, from transportation to reality itself. And just when it seemed the investigation had reached its deepest level, another apparent solution appeared. A solution even more seductive than wormholes. A solution promising to escape cosmic isolation entirely. For a brief moment, it looked as though humanity had finally found a way around the universe's limitations. But the next chapter would reveal why some answers are more dangerous than the mysteries they attempt to solve. The mystery was becoming larger than the universe itself. There is a moment that appears in nearly every great investigation. The evidence aligns. The clues fit together. The mystery seems solved. Investigators begin relaxing. The search appears complete. Then a new piece of evidence arrives, and everything changes. Cosmology has experienced this moment repeatedly, again and again. Scientists approached what looked like a final explanation. Again and again, the universe revealed a deeper layer. The idea that emerged next felt different, more ambitious, more radical, and for a brief time it seemed capable of resolving multiple mysteries simultaneously. The proposal centered on a simple observation. Quantum mechanics already permits phenomena that appear impossible from an ordinary perspective. Particles become correlated across enormous distances. Probabilities replace certainties. Reality behaves in ways that challenge intuition. Perhaps, some researchers wondered, the solution to cosmic separation lies not in space-time itself, but in the quantum world beneath it. The suggestion was seductive. Because quantum mechanics often appears to violate ordinary notions of distance, two particles can become entangled. Their properties remain correlated even when separated by vast regions of space. Einstein famously disliked the implication. He referred to it as spooky action at a distance. The phrase survived because it captured a genuine discomfort. The universe seemed to be hiding connections where none should exist. At first glance, entanglement looked like the perfect escape route. If quantum systems remain linked across distance, perhaps communication can bypass light speed limits. Perhaps information can leap across the cosmos. Perhaps the barriers revealed throughout our investigation are not fundamental after all. The possibility generated excitement. Science fiction embraced it enthusiastically. Popular discussions often portrayed entanglement as a kind of instantaneous connection, a hidden bridge between distant locations, a cosmic shortcut. For a moment, it appeared the mystery might finally be unraveling. Then, physicists examined the details. The result was disappointing and fascinating. Quantum entanglement creates correlations. It does not create controllable communication. The distinction is crucial. Imagine two sealed envelopes prepared in advance. Open one and discover a red card. Instantly, You know the other envelope contains a blue card. Information has been revealed, yet no message was transmitted. No signal travelled. No communication occurred. Entanglement behaves similarly. Measurements become correlated, but the correlations cannot be used to send information faster than light. Nature once again preserves the barrier. Another apparent loophole closes. Another solution dissolves. The pattern had become familiar. Every time the universe seems ready to surrender its secrets, another limitation appears. Yet quantum mechanics continued producing surprises, because while entanglement failed to solve communication, it hinted at something deeper, something potentially revolutionary. Researchers began noticing unexpected connections between quantum information and space-time geometry. The relationship seemed bizarre, almost impossible. Yet the mathematics repeatedly pointed in the same direction. Information and geometry might be linked. Not metaphorically, fundamentally. Imagine discovering that roads and conversations are different manifestations of the same underlying process. The idea sounds absurd, yet something similar may be happening in fundamental physics. Some theories suggest that space-time itself emerges from patterns of quantum information. The geometry of reality could be a consequence of deeper informational relationships. If true, distance becomes less fundamental. Space becomes less fundamental. Perhaps even time becomes less fundamental. The implications were staggering. For the first time, physicists glimpsed a framework in which the familiar universe might emerge from something deeper and more abstract. A hidden substrate beneath reality. An invisible architecture supporting existence. At first, this seemed like the breakthrough everyone had been seeking. The missing foundation. The final explanation. Then the complications arrived, because every attempt to construct a complete theory encountered unresolved problems, mathematical difficulties, experimental limitations, conflicting interpretations. The deeper investigators descended, the more elusive certainty became. The mystery expanded again. And once more, a false ending emerged. The answer appeared close, then retreated. Yet even as these theoretical debates unfolded, another clue was quietly transforming cosmology. A clue hidden within the future, not the past. For most of history, astronomy focused on origins. Where did the universe come from? How did galaxies form? What happened after the Big Bang? Increasingly, scientists began asking a different question. Where is the universe going? The answers proved unsettling, because cosmic expansion is not merely changing the present. It is shaping the future, and that future contains consequences more dramatic than most people realize. Consider a civilization living 100 billion years from now. Not millions, not billions. 100 billion. The night sky would look radically different. External galaxies would largely disappear beyond the cosmic horizon. Evidence for expansion would fade. Ancient light would weaken. Many clues supporting modern cosmology would become inaccessible. Future scientists could inherit a universe stripped of its own history, a cosmos concealing its origins. The thought is haunting. Knowledge itself appears temporary. The evidence available today may not remain available forever. Humanity may exist during a rare observational window, a brief interval when reality still leaves enough traces to reconstruct its story. This realization changed the investigation profoundly. The mystery was no longer just about whether we can reach distant regions. It became a question of whether future observers can even know they exist. Entire chapters of reality may gradually vanish from evidence, not from existence, from knowledge, and that distinction echoed a recurring theme. The universe continually separates existence from accessibility, reality from observation, truth from evidence. Again and again, the same pattern emerged. Not everything that exists can be reached. Not everything that exists can be seen. Not everything that exists can be known. For a moment, this seemed like the final lesson, the ultimate limitation, the unavoidable conclusion. Then another possibility appeared, one even stranger than quantum entanglement, one involving shortcuts through space-time so dramatic that they challenge the meaning of distance itself. Wormholes, warp geometries, cosmic tunnels, ideas once dismissed as fantasy, yet increasingly difficult to ignore completely. The investigation was about to enter its most speculative territory, and there, the mystery would become stranger than anyone expected. The answer seemed obvious. It wasn't. Every civilization tells stories about hidden passages, secret tunnels beneath mountains, forgotten doors inside ancient cities, invisible paths connecting distant places. The details change. The theme remains. Human beings are fascinated by shortcuts, perhaps because distance has always imposed limits. A shortcut promises freedom from those limits, a way around obstacles rather than through them. By the time our investigation reached the deepest questions of cosmology, the temptation had become irresistible. The universe seemed too large. Light seemed too slow. Expansion seemed too relentless. Surely there must be another route, some hidden pathway concealed within reality itself. Remarkably, modern physics does not completely reject the possibility. In fact, it occasionally hints at it. The clues emerge from Einstein's equations, the same equations responsible for black holes, gravitational waves, and cosmic expansion. Again and again. Researchers discovered something curious. Space-time is far more flexible than intuition suggests. Most people imagine space as an empty stage, a passive background, a place where events occur. Relativity revealed a different picture. Space bends, stretches, twists, curves. It behaves less like a rigid framework and more like a dynamic fabric. And once a fabric can bend, strange possibilities emerge. Imagine drawing two cities on a sheet of paper. Travelling normally requires crossing the distance between them. Now fold the paper until the cities touch. The journey becomes almost instantaneous. Nothing travelled faster. The geometry changed. This simple image lies at the heart of the wormhole concept. A wormhole is often described as a tunnel through space-time, a bridge connecting distant regions, a shortcut that reduces enormous separations to manageable lengths. The idea sounds fantastical, yet it emerged directly from serious mathematical investigations. In 1935, Einstein and physicist Nathan Rosen described structures now known as Einstein-Rosen bridges. The concept fascinated generations of researchers, not because wormholes were known to exist, because the equations allowed them. The distinction is important. Physics frequently permits possibilities that nature never realizes. Mathematical existence does not guarantee physical reality. Still, the door remained open, and that alone was extraordinary. For decades, wormholes occupied an unusual position, neither accepted nor dismissed, neither science nor fantasy, possibility suspended between worlds. Then theoretical investigations became more sophisticated. Researchers discovered that traversable wormholes capable of carrying travelers safely, required unusual conditions. Very unusual conditions. Once again, exotic energy appeared. Negative energy densities, configurations unlike anything observed in ordinary matter. The same obstacle haunting walk drives returned. Nature seemed willing to sketch the blueprint. It refused to provide the materials. The pattern had become familiar. A solution appears. A closer examination reveals another barrier. Yet despite these difficulties, wormholes changed the conversation because they demonstrated something profound. Distance is not necessarily fundamental, at least mathematically. The geometry of spacetime can alter effective separation. Two locations enormously distant in ordinary space might become neighbors under the right conditions. This realization expanded beyond wormholes themselves. It suggested that our intuitive understanding of distance may be incomplete. Reality could possess structures hidden beneath everyday perception. Invisible connections, deeper geometries, relationships inaccessible through ordinary experience. And surprisingly, modern physics keeps discovering hints of such possibilities. Some theoretical frameworks propose that space-time itself emerges from networks of underlying connections. Others suggest that geometry and information are deeply intertwined. Again and again, the same idea appears. The visible universe may not be the whole story. Something deeper may exist beneath the familiar landscape. At first glance, this sounds like a direct path to solving our mystery. If hidden structures exist, perhaps cosmic isolation disappears. Perhaps light speed ceases to matter. Perhaps distant galaxies become accessible. For a moment, the dream feels plausible. Then the scale returns. Because even if wormholes exist, another problem emerges. Finding them, creating them, stabilizing them, understanding them. Each challenge rivals the original mystery. Imagine discovering that secret tunnels exist beneath a continent. Wonderful news. unless every entrance lies buried beneath mountains, protected by impossible locks, and located using maps nobody possesses. The existence of a shortcut does not guarantee access, and cosmology repeatedly confronts this distinction. Possibility and practicality are not the same. Yet wormholes revealed something invaluable. They shifted attention away from speed, toward structure, toward geometry, toward the foundations of reality. The investigation was evolving again, and while physicists debated space-time tunnels, another realization emerged, one perhaps even more important, because wormholes, warp drives, and exotic geometries all share a common feature. They attempt to overcome distance. But what if distance is not the deepest problem? What if even perfect shortcuts fail to solve the central mystery? Consider a civilization capable of crossing the observable universe instantly. An extraordinary achievement. Yet the observable universe is not necessarily the whole universe. Expansion continues. Horizons persist. Unknown regions remain hidden. Ancient epochs remain inaccessible. Information limitations remain. The deeper questions survive. Travel alone cannot solve them. This realization transformed the investigation once again. The original problem had seemed straightforward. Light speed is too slow. Now the issue appeared far more profound. Even if light speed could be bypassed, reality itself might still resist complete understanding. The universe was not merely imposing a transportation limit, it was imposing a knowledge limit. Again and again, every path led back to the same conclusion. Existence exceeds observation. Reality exceeds accessibility. Truth exceeds evidence. The pattern appeared everywhere. In horizons, in expansion, in quantum uncertainty, in cosmic origins, in the future fate of galaxies. Every clue pointed toward a remarkable possibility. The universe may be fundamentally larger than any observer can fully comprehend, not temporarily, permanently. And if that is true, then the mystery of light speed was never really about motion. It was about perspective, about what any civilization can know, about the boundaries separating awareness from reality. The implications were enormous, and they led directly into the third and perhaps most deceptive false ending of the investigation. Because just when it seemed that hidden geometries offered an escape, physicists discovered a complication so profound that it forced them to reconsider the meaning of reality itself. The mystery was about to become even stranger. By now, the investigation had crossed a remarkable threshold. The mystery no longer resembled the question with which we began. At first, everything seemed simple. Could humanity travel fast enough to explore the universe? That was the puzzle. That was the challenge. The answer appeared technological. Build better engines. Generate more energy. Reach greater speeds. Problem solved. Instead, every clue pointed elsewhere, toward space-time, toward information, toward horizons, toward limits embedded within reality itself. And yet, one final possibility continued to tempt physicists. Perhaps the universe is larger than we can observe. Perhaps much of reality remains hidden. But maybe that hidden reality is not truly separate. Maybe everything is connected through a deeper structure, a hidden framework beneath the visible cosmos. A final answer seemed close, a grand unification of the mystery. For a moment, it looked achievable. Then the evidence became stranger. The clue emerged from one of the most unexpected places imaginable: black holes. For decades, black holes appeared to be endpoints, gravitational graves, objects so dense that not even light can escape. Interesting. Certainly important, undoubtedly, but largely isolated from broader questions about cosmic knowledge. Then, physicists discovered something extraordinary. Black holes seem obsessed with information. The realization began with a paradox. According to quantum mechanics, information cannot simply disappear. The universe preserves it. According to classical descriptions of black holes, information crossing the event horizon appears lost. The two conclusions conflict. One of them must be incomplete. The contradiction became known as the black hole information paradox. At first glance, it sounded like a technical problem, an obscure dispute among theoretical physicists. In reality, it became one of the deepest mysteries in modern science, because resolving the paradox required understanding what information truly is. And once that question emerged, everything changed. Researchers discovered astonishing relationships between gravity, entropy, geometry, and information. Again and again. The mathematics pointed toward an unsettling possibility. Space-time itself might emerge from informational structures, not metaphorically, literally. The geometry of reality could arise from patterns of information. The implications were staggering. Imagine discovering that a city is not built from bricks. Instead, the bricks emerge from deeper relationships. The apparent foundation becomes a consequence. Something similar may be true of space-time. If so, then distance is not fundamental. Space is not fundamental. Perhaps even time is not fundamental. The familiar universe becomes an emergent phenomenon, a visible layer generated by deeper processes. For a brief period, this felt like the breakthrough. The hidden architecture had been found. The mystery was finally yielding. The speed of light, cosmic horizons, expansion. Everything might ultimately derive from informational principles. The answer seemed elegant, powerful, almost complete. Then another question emerged, and it shattered the illusion of closure. If space-time emerges from something deeper, what does that deeper thing emerge from? The problem returned immediately. One layer lower, one level deeper. The mystery survived again. The pattern repeated with almost cruel consistency. Every solution exposed the larger question. Every foundation revealed another beneath it. The universe behaved like an endless series of horizons. Reach one, discover another, cross it, find a larger one waiting. This was the third false ending, the most subtle of all, because it did not fail through contradiction. It failed through incompleteness. The explanation worked, yet it left the deepest question unanswered. Why does reality possess this structure at all? Nobody knows, and perhaps that ignorance is more important than any answer, because it reveals something fundamental about scientific exploration. Science does not move toward certainty, it moves toward better mysteries. The investigation had begun with stars. Now it confronted the foundations of existence, and still the mystery remained. The scale escalation was breathtaking. Humanity once worried about crossing oceans, then planets, then star systems, then galaxies. Now the question concerned the structure of reality itself. The journey had expanded far beyond its original scope. Yet one final transformation remained, the most important transformation. Because throughout this investigation, we have largely focused on the universe, its size, its structure, its horizons, its limitations. But what do those limitations mean for us, for observers, for intelligence, for civilizations trying to understand their place within existence? The question changes everything, because a universe that cannot be fully explored is not merely a scientific fact. It is a philosophical one. Imagine being born inside an endless library. The shelves stretch beyond sight. Most books remain unreachable. Many sections are permanently inaccessible. Entire wings vanish into darkness. Would the library be a failure? Or would the mystery itself become part of its meaning? The same question applies to the cosmos. For centuries, humanity assumed that complete understanding represented the ultimate goal, a final theory, a final explanation, a complete map. Modern cosmology increasingly challenges that assumption. The universe may not be constructed in a way that permits total comprehension, not because humans are flawed, because finite observers may always confront infinite horizons. The limitation is structural, and strangely, that realization does not diminish the value of discovery. It enhances it. Every observation becomes precious. Every clue becomes significant. Every glimpse beyond a horizon becomes remarkable, because certainty is no longer guaranteed. Knowledge becomes exploration rather than possession, a process rather than a destination. The universe stops being a puzzle to finish. It becomes a mystery to participate in. And that shift prepared the investigation for its final act, the existential payoff. Because the question is no longer whether light speed is fast enough. The question is what the existence of such limits reveals about reality itself. About intelligence, about humanity, about the strange role observers play within an incomprehensibly large cosmos. The answers would lead beyond astronomy, beyond physics, beyond cosmology, toward something far more personal. The real mystery was waiting there all along. There is a strange possibility hidden within the future, a possibility so quiet that it rarely appears in discussions about space exploration. No explosions. No cosmic catastrophe, no dramatic collapse of reality. Instead, something far subtler. The universe may simply become forgetful, not consciously, not intentionally, but through the gradual disappearance of evidence. Throughout this investigation, we've encountered the same pattern repeatedly. Galaxies drift apart, horizons expand, information becomes inaccessible, ancient light fades, connections weaken. Each process seems manageable on its own. Together, they reveal a remarkable truth. The universe is not merely growing, it is growing beyond memory. Imagine standing inside an ancient city while every road leading outward slowly lengthens. At first, travel remains possible. Then it becomes difficult. Eventually, neighboring cities disappear from practical reach. The cities themselves survive. The network does not. History fragments. Knowledge fragments. Civilizations inherit smaller and smaller pictures of the larger world. Cosmology suggests something similar may happen on the grandest scales imaginable, and the implications are profound, because memory is not merely a biological phenomenon. Civilizations possess memory. Science possesses memory. The universe itself preserves traces of its past. Ancient photons crossing billions of years, fossil radiation, elemental abundances, galactic structures. Every clue functions as a record, a remnant, an echo. Without such traces, reconstruction becomes impossible. A detective requires evidence. An archaeologist requires artifacts. A cosmologist requires signals. Remove the evidence, and knowledge begins to dissolve. Future astronomers may confront precisely this situation. Imagine a civilization emerging trillions of years from now. Its scientists build observatories, map the sky, study the cosmos. They are intelligent, curious, methodical, just like us. Yet, the universe they observe differs dramatically from ours. Most galaxies have vanished beyond the cosmic horizon. The microwave background has stretched into near undetectability. Evidence for cosmic expansion has largely disappeared. The visible universe appears smaller, simpler, more isolated. Their conclusions might be entirely different, not because they are less capable, because they possess less evidence. This possibility remains one of the most haunting consequences of modern cosmology. Knowledge depends upon circumstance. The timing of observation matters. Humanity may exist during a uniquely informative epoch, a brief interval when reality still exposes enough clues to reconstruct its history. Before us, no observers existed to ask the questions. After us, much of the evidence may fade. We occupy a narrow window between ignorance and obscurity. The realization feels almost poetic, yet it emerges directly from physics, and it changes how we view the cosmos. For centuries, people imagined scientific progress as an endless ascent, knowledge increasing continuously, mysteries steadily disappearing. The universe presents a more complicated picture. Some mysteries yield, others deepen. Some evidence appears, other evidence vanishes. Understanding grows. Access shrinks. The process is not one-directional. Reality gives with one hand and removes with the other. And nowhere is this more apparent than in the future fate of galaxies. The Milky Way and the Andromeda Galaxy are currently moving toward one another. Billions of years from now, they will merge. Their stars will intermingle. Their structures will transform. A new galaxy will emerge. Astronomers sometimes call this future system Milkomeda, a name that sounds playful. Its implications are profound, long after the merger. External galaxies will continue retreating beyond visibility, eventually. Milkomeda may stand effectively alone, an island universe surrounded by darkness. Future observers living within it might never suspect that countless galaxies once filled the sky. The evidence will be gone. Not hidden, gone. The image is haunting, an immense cosmos gradually withdrawing from view, not through destruction, through expansion. A silent retreat. And this raises a troubling question. How much of reality has already disappeared from us? Human beings often think of themselves as late arrivals, and in many respects, we are. The universe existed for billions of years before Earth formed, before life appeared, before intelligence emerged. Entire chapters unfolded without witnesses. What information vanished during those eras? What evidence crossed horizons before observers evolved? What traces disappeared forever? We cannot know. The irony is striking. Science reconstructs the past with remarkable success. Yet some portions of cosmic history may already be irretrievable, lost not because they were unimportant, lost because information failed to survive. Again and again, the investigation returns to the same theme: information, not matter. Not energy, information. Reality appears organized around its flow, its preservation, its disappearance. The speed of light governs information. Cosmic horizons restrict information. Expansion isolates information. Black holes challenge our understanding of information. Every major mystery points toward the same underlying concept. And once this pattern becomes visible, another realization follows. The universe may not fundamentally be a collection of objects. It may be a collection of relationships, connections, exchanges. Information networks spanning space-time. Stars matter because they emit information. Galaxies matter because they preserve information. Observers matter because they process information. Without information, reality becomes inaccessible. Without accessibility, existence and knowledge diverge. The distinction may be the most important lesson of all, because our original question concerned speed, light speed, travel, exploration. Now the investigation has arrived somewhere unexpected. The deeper issue is not how quickly we move, it is how much reality remains available to know. And the answer appears sobering. No matter how advanced a civilization becomes, portions of existence may remain forever beyond reach. Not because intelligence fails, because horizons exist, because evidence fades, because the universe grows larger than memory itself. The realization could feel discouraging, yet it contains another interpretation, a more hopeful one, because if complete knowledge is impossible, then discovery never ends. The mystery survives. The search continues. And perhaps that is precisely what makes the universe meaningful to explorers. But before reaching that conclusion, one final horizon remains to be examined. The horizon separating scientific limits from existential implications. The horizon separating the cosmos from ourselves. And beyond it lies the deepest question of the entire investigation. What does it mean to be a finite observer inside an infinite mystery? The answer would take us beyond astronomy entirely. At the beginning of this story, the universe appeared to present a practical challenge, a problem of transportation, a question of engineering. Could humanity build a machine fast enough to cross the cosmos? It seemed like a straightforward investigation. Now, standing at the edge of everything we have uncovered, the question looks very different, because every clue pointed toward the same unsettling conclusion. The ultimate horizon is not physical. It is epistemological, a horizon of understanding, a boundary separating what can be known from what may remain forever hidden. And unlike the horizons encountered by explorers of Earth, this one does not necessarily retreat when approached. For centuries, scientific progress created a powerful expectation. Every mystery seemed temporary. Lightning became electricity. Disease became biology. Planets became worlds. Unknown regions became mapped territories. The lesson appeared universal. Ignorance shrinks. Knowledge expands. Reality becomes increasingly understandable. Cosmology complicates that story, not because science has failed, because science has succeeded. The deeper we investigate the universe, the more clearly we perceive its boundaries. And those boundaries are extraordinary. Consider what we now know. The observable universe is not the entire universe. Most of reality may lie beyond observation. Cosmic expansion continuously removes information from reach. Ancient epochs remain hidden behind primordial barriers. The future would erase evidence available today. Even the structure of space-time may emerge from deeper principles we do not yet understand. Every discovery widens the map. Every discovery also reveals a larger unknown. The pattern resembles standing atop a mountain range. Each summit promises a final view. Each summit reveals another horizon. The process repeats endlessly. And perhaps that repetition contains the real lesson. Human beings often imagine knowledge as possession, a collection of answers, a completed inventory of truths. The universe suggests something different. Knowledge may be relational rather than absolute, a dialogue rather than an ownership, a continuous interaction between observers and reality. This distinction matters because complete understanding may not be the destination. Participation may be. Imagine entering a vast cathedral whose architecture extends beyond visibility. You can explore it, measure it, study portions of it. You can learn remarkable things. Yet no single observer ever sees the entire structure at once. The limitation does not diminish the cathedral, nor does it invalidate exploration. The mystery remains part of the experience. The universe may function similarly, not as a puzzle waiting for final assembly, but as an inexhaustible landscape of discovery. This idea becomes particularly striking when considering intelligence itself. For billions of years, the cosmos evolved without observers capable of reflecting upon it. Stars formed, galaxies collided, black holes grew, the universe unfolded in silence. Then, on a small planet orbiting an ordinary star, matter became aware of itself. Atoms organized into cells, cells into organisms, organisms into minds, and eventually, those minds began asking questions. The transformation is astonishing when viewed from a cosmic perspective. The universe developed a mechanism for self-observation, not perfect observation, not complete understanding, but observation nonetheless. Every telescope, every equation, every experiment, every act of curiosity, all represent reality examining itself through conscious beings. The thought is philosophical, yet it emerges naturally from the investigation. Because observers occupy a peculiar position, we are simultaneously insignificant and essential. Insignificant in scale, essential in function. The Milky Way would continue existing without humanity. The observable universe would remain vast. Galaxies would continue drifting toward horizons. Nothing about cosmic expansion depends upon us. And yet, without observers, there would be no questions, no interpretations, no understanding, no awareness of the mystery. The universe contains structures larger than comprehension, yet comprehension itself remains one of the rarest structures we know. That realization changes how we view limitations. The speed of light once appeared frustrating. Now it appears informative. Cosmic horizons once seemed restrictive. Now they appear revealing. Boundaries teach us about the structure of reality. They expose the rules underlying existence. Without limits, many of the universe's deepest properties would remain invisible. Paradoxically, obstacles become clues. Every horizon teaches us something about what lies beyond it. And this returns us to the original mystery. Why isn't light speed fast enough? The simplest answer is obvious. The universe is too large. But the deeper answer is more interesting. Light speed is not insufficient, because the cosmos is merely big. It is insufficient because reality appears structured around limits. Limits of travel, limits of communication, limits of observation, limits of knowledge. Again and again, the same pattern emerges. The universe permits exploration. It resists completion. It invites investigation. It denies finality. And perhaps that is not a flaw. Perhaps it is a feature, because a completely knowable universe would eventually cease being mysterious. A completely accessible universe would eventually cease being exploratory. A completely solved universe would eventually cease generating discovery. Instead, reality appears to preserve horizons, forever receding frontiers, endless layers, questions behind questions. The mystery survives every explanation. Not because science fails, because reality continues. And that realization brings us to the final chapter. The chapter where the investigation turns inward, away from galaxies, away from horizons, away from cosmological models, toward the deeper meaning hidden beneath the entire story. Because the true significance of light speed may never have been about travel at all. The final clue was waiting much closer to home. At the beginning of this investigation, the question seemed almost practical. If humanity could travel at the speed of light, would that finally be enough? Would the stars become reachable? Would the galaxy become navigable? Would the universe finally open itself to exploration? It felt like a question about movement, about technology, about transportation. Now, after following the evidence across cosmic horizons, ancient light, expanding space-time, quantum paradoxes, and the limits of observation, the question looks entirely different. Because the mystery was never really about speed. It was about perspective. The universe forced us to confront something far more profound than distance. It forced us to confront scale, not merely physical scale, existential scale. The scale separating finite observers from an apparently inexhaustible reality. For thousands of years, humanity has lived inside a recurring narrative. A frontier appears. The frontier is crossed. A larger frontier appears. The process repeats. Ancient sailors crossed oceans. Explorers crossed continents. Astronomers crossed the solar system with telescopes. Modern observatories crossed billions of light years through observation. Every generation believes it is approaching the edge. Every generation discovers another horizon. Cosmology has revealed that this pattern may not be temporary. It may be fundamental. Reality itself appears constructed in layers, and every layer conceals another. The Earth was not the center. The solar system was not the center. The Milky Way was not the center. The observable universe may not be the center. Again and again, certainty dissolved into larger contexts. The lesson is remarkably consistent. The closer we move toward understanding everything, the larger everything becomes. That realization can feel discouraging at first. The universe is too large, too old, too complex, too distant, too mysterious. Even light, the fastest traveler known to nature, cannot bridge all of its separations. Entire regions remain inaccessible. Entire histories remain hidden. Entire futures remain unknowable. But perhaps this is the wrong way to interpret the evidence, because hidden within every limitation we encountered was another truth. The universe allows partial understanding, and partial understanding is extraordinary. Consider what humanity has already accomplished. A species that evolved on a small rocky world now measures the age of the cosmos, detects collisions between black holes, maps structures billions of light years away, reconstructs conditions from nearly 14 billion years in the past, predicts the future evolution of galaxies, discovers planets orbiting distant stars, investigates the geometry of space-time itself. These achievements are astonishing, not because they solve every mystery, because they exist at all. The universe never promised to be understandable, yet somehow portions of it are. That may be one of the strangest facts we have encountered. Reality contains enough order for minds to investigate it. Enough structure for science to function, enough coherence for understanding to grow. And perhaps that is the true miracle hidden beneath the investigation. Not that the universe is knowable, that any part of it is knowable at all. Because from another perspective, consciousness itself appears improbable. Matter organizing into awareness. Awareness organizing into curiosity. Curiosity organizing into science. Science organizing into cosmology. The chain is remarkable. The cosmos created observers capable of wondering about the cosmos, and those observers discovered that reality exceeds them. The irony is beautiful. The more accurately we measure the universe, the less central we appear. Yet the act of measurement remains extraordinary. The universe may be vast beyond comprehension, but comprehension exists. That fact matters. Throughout this story, we repeatedly encountered horizons, boundaries beyond which information cannot travel, limits beyond which observation cannot reach, invisible walls woven into space-time. At first, they appeared restrictive. Now, they look different. Horizons define exploration. Without horizons, exploration ends. Without mysteries, discovery ends. Without unknowns, curiosity loses its purpose. The universe seems determined to preserve the unknown, not through hostility, not through concealment, through scale, through depth, through endless complexity. Every answer generates new questions. Every discovery reveals larger contexts. Every horizon conceals another beyond it. And perhaps that is exactly what a living scientific civilization needs. Not final certainty, endless investigation. Imagine for a moment that humanity eventually achieves everything. Interstellar travel, galactic exploration, mastery of energy, control over space-time. Even then, the deeper mysteries survive. What lies beyond the observable universe? What created the conditions for inflation? Why do physical laws possess their current values? What is the ultimate nature of information? Why does reality exist at all? The questions continue. The horizons remain. The investigation never truly ends. And that brings us back to the title of this story. If we could travel at light speed, it still wouldn't be fast enough. Not because the engines fail, not because the distances are too large, not even because the universe is expanding. Light speed would not be enough, because the mystery itself is larger than movement. Reality contains more than any traveler can visit, more than any civilization can observe, more than any theory can fully capture. The cosmos exceeds every map, every model, every explanation. And yet, despite that fact, or perhaps because of it, we continue searching. We build larger telescopes, develop deeper theories, ask harder questions, push farther into the darkness. Not because we expect the mystery to disappear, because the mystery is the destination. Perhaps that is the hidden truth buried beneath the entire investigation. The real lesson may not be that the universe is too large for us. The real lesson may be that curiosity is larger than any horizon. Maybe that is why intelligence emerged at all. Maybe that is why observers exist. To stand inside an incomprehensibly vast reality and keep asking questions anyway. And if that is true, then the speed of light was never the most important limit. The most important fact is that, against all odds, the universe produced beings capable of wondering what lies beyond it. Perhaps that is enough. Or perhaps, like every answer in this story, it is only the beginning. And as we bring this journey to a close, I'd love to hear your thoughts. If humanity could somehow overcome every technological obstacle imaginable and reach the speed of light tomorrow, where would you choose to go first? A nearby star, the center of the Milky Way, or perhaps somewhere even farther, beyond the galaxies we know today? Leave your answer in the comments below. I always enjoy reading the ideas, theories, and questions that emerge from these conversations. And if you enjoy exploring the deeper mysteries of the universe, the questions that grow larger the more we investigate them, consider subscribing and joining us for future journeys into space, time, and the hidden structure of reality. Until next time, keep looking up. The universe still has many secrets left to reveal.